Skittles, Sour Patch Kids, and Starburst are mass-produced in candy factories that move faster than your sugar rush. From molten sugar vats to flavor-blasting machines and lightning-fast packaging lines, every piece is built for color and taste. Today, we're going inside secret factories to showcase the process of how these legendary candies are really made. The journey of a Skittle begins in the raw material silos of a large-scale confectionery factory. The primary ingredient is refined granulated sugar, delivered by truck or rail in bulk and stored in food-grade silos. Other key components include corn syrup, hydrogenated vegetable oil, fruit acids, natural and artificial flavorings, colors, and modified starch. All materials are received under strict quality protocols and logged into inventory for traceability and batch control. The first major production step is the formation of the Skittles inner chewy center. This core is not hard like a jawbreaker, nor soft like a gumdrop. It's dense and elastic, made through a carefully controlled process. In giant heated mixing kettles, sugar and corn syrup are combined and brought to a boil, creating a thick, sticky syrup. The syrup is cooked to a precise temperature, usually between 125 degrees and 140 degrees, which determines the final texture of the candy. This temperature control is critical. Undercooking results in a gooey center. Overcooking leads to brittleness. Once the syrup reaches its target consistency, it is cooled slightly and blended with emulsifiers, acids like citric or malic acid, and fruit flavor concentrates. The mixing is done under vacuum to remove air bubbles and prevent crystallization. At this point, food-grade color can be added if the core is meant to carry some of the hue, although in many variations, the center remains pale. Now, the warm, pliable candy mass is transferred to a batch roller, a piece of equipment that rolls the candy into a thick rope. This rope is gradually tapered and elongated by rope sizes until it reaches the diameter of a single Skittle core. The rope is fed into a die-forming machine which slices the rope and punches each segment into the signature lentil-shaped candy pieces. These soft, uncoated cores are called centers, and they're left to rest on large trays until they reach room temperature and stabilize. Meanwhile, another vital component is being prepared: the starch molding beds. Though Skittles aren't molded like gummy bears, modified cornstarch trays may still be used to stabilize the centers during drying or early coating steps. The trays absorb surface moisture and maintain product shape, especially in humid climates. Once stable, the centers are sieved and transferred to the coating department. This is where the visual identity of Skittles takes form. The centers are loaded into large rotating coating pans, also known as draggy pans. These stainless steel drums slowly tumble the candies while various coating liquids are added in thin layers. The first coating is a base of sugar syrup, consisting of dissolved sugar, glucose, and sometimes a binding agent like gum arabic. A spray arm applies the syrup as the drums turn, allowing the syrup to evenly coat the surface of each core. Once applied, dried air is blown over the tumbling candies to evaporate excess moisture and begin hardening the sugar coating. This process is repeated many times, layer upon layer. A typical Skittle may have dozens of micro layers of sugar applied, giving it that perfect shell thickness. If the process is rushed, the shell becomes uneven or overly brittle. If too slow, production volume suffers. Once the shell reaches the desired size and firmness, coloring agents are introduced. This is done either through pre-colored sugar syrups or by adding FDA-approved food colorants directly into the pans, mixed with additional layers of coating solution. Each flavor, strawberry, lemon, lime, orange, grape, receives its own specific colorant blend, with closely monitored dosing to maintain visual consistency. After coloring, flavoring is added. This is one of the most technically challenging steps. While the inner core contains some flavor, Most of the intense fruit punch you taste comes from the outer shell. A flavor mist, a blend of volatile fruit esters and solvents, is sprayed in measured amounts across the coating pans. This method ensures that the flavor sits close to the surface and hits the palate immediately upon biting. The flavor compounds must be handled carefully to avoid loss due to evaporation or cross-contamination between varieties. The candies are then dried one final time and transferred to the polishing stage. This is what gives Skittles their brilliant, glassy shine. The tumbling pans are now sprayed with tiny amounts of carnauba wax, a natural plant-based wax derived from the leaves of the Brazilian palm. It's safe to eat and commonly used in confections and pharmaceuticals. Just a fraction of a gram per kilogram of product is enough to create that smooth, glossy finish. After waxing, the Skittles are tumbled for several minutes to distribute the shine uniformly across all surfaces. Now comes branding. Each Skittle is printed with a tiny white S using an edible ink and a pad printing system. Pad printing involves a soft silicone pad pressing an inked image onto a curved surface. It's incredibly precise, printing thousands of candies per minute, each one perfectly aligned. The ink is made from food-grade titanium dioxide and FDA-approved pigments. This is one of the most visually controlled stages of production. High-speed cameras scan every printed candy, and those missing a clear S or printed off-center are rejected. From here, the finished candies move to the packaging line. First, they are sorted by flavor blend and dosed into small packaging hoppers. These hoppers connect to form-fill-seal machines that create bags from rolls of plastic film. Each bag is filled with a standard weight of Skittles, typically 2 Oz to 4 Oz for retail packs, and sealed with heat and pressure. Some facilities use nitrogen flushing to displace oxygen inside the bag, which helps preserve flavor and extend shelf life. Once sealed, each bag is date-coded with the production batch and expiration date. Barcode scanners check each unit before the bags are automatically grouped into cartons. These cartons are sealed, labeled, and stacked by robotic palletizers into outbound shipping units. Before they leave the factory, selected cartons are pulled aside for final quality testing. In the QA lab, technicians measure key product characteristics: coating thickness, flavor balance, hardness, color matching, and packaging integrity. Texture analyzers check the chewiness. Gas chromatography systems can be used to test flavor compound retention, and trained sensory panelists evaluate taste and mouthfeel in controlled booths. Each batch is compared to a master profile, ensuring that Skittles remain consistent across all production locations. Behind all this, an extensive network of automated controls and digital monitoring systems governs every stage. Programmable logic controllers manage syrup temperatures, coating cycles, drying airflow, and wax dosing. Manufacturing execution systems track ingredient usage, monitor machine downtime, and tie every product back to its raw material batch numbers. These systems also ensure compliance with food safety standards like ISO 22000, HACCP, and FDA regulations. Plant sanitation is equally rigorous. Equipment is washed and sanitized between flavor batches to prevent cross-contact. Color changeovers require additional cleaning to avoid visual contamination. Air filtration, stainless steel surfaces, and strict personnel hygiene zones maintain product integrity and allergen control throughout the process. Environmental sustainability is also a growing focus. Modern Skittles factories have invested in energy-efficient dryers, LED lighting, and water reclamation systems. Off-spec product and starch dust are collected and diverted to non-food uses or animal feed where allowed. Recycling programs manage the extensive film waste from packaging operations. First they're sour, then they're sweet. Sour Patch Kids have become a staple in the world of chewy confections, instantly recognizable for their soft texture, bold fruit flavors, and that unforgettable sour sugar coating. But while these tangy little figures may look playful on the outside, their production process is anything but simple. Behind the brightly colored packaging lies a highly controlled, highly automated manufacturing environment where starch molds, candy cookers, acid coatings, and sugar crystallization must work in flawless harmony to deliver millions of perfectly shaped Sour Patch Kids each day. The story begins with the most essential ingredient in any gummy candy: sugar. Granulated sucrose is delivered to the candy factory in bulk, often by tanker trucks, and stored in stainless steel silos. From there, it's transported via pneumatic conveyors into large cooking tanks, where it's blended with glucose syrup, water, and modified food starch. This syrup base is the backbone of Sour Patch Kids' unique texture. It must be thick enough to hold shape, but elastic enough to chew cleanly. Never rubbery, never too soft. The mixing tanks are fitted with agitators and are heated to carefully controlled temperatures, typically between 115 degrees Celsius and 130 degrees Celsius. At this stage, a gelatin or pectin base may be added, depending on the product variation and dietary requirements. Gelatin offers a classic elastic chew, while pectin provides a softer bite and allows for vegetarian options. Food-grade acids, usually citric, tartaric, and malic acid, are incorporated into the mixture in precise amounts to achieve that characteristic mouth-puckering sourness. The acids must be balanced carefully, not just for flavor, but because they can impact gelatin structure if added too early or in excessive concentration. Once the candy syrup reaches its target temperature and consistency, it's filtered to remove air bubbles and is pumped to the starch molding department, a critical step in the gummy candy world. Here, trays filled with a layer of fine, dry cornstarch are used to hold the shape of each candy. Using a machine called a mogul, thousands of molds are stamped into the starch bed in a single motion. Each imprint is shaped like the familiar Sour Patch Kid figure: a rounded head, short arms, and stubby legs. The hot candy syrup is deposited into these starch molds through high-precision nozzles. Depositors are calibrated to release exact volumes into each cavity, down to fractions of a gram. If the flow rate is even slightly off, candies will be misshapen or oversized, an issue that could clog packaging lines or impact drying time. As the molds are filled, the trays are conveyed into drying tunnels, where they remain for 24 to 48 hours, depending on humidity and composition. Warm, dry air circulates through these tunnels, slowly removing moisture from the candies while allowing them to firm up and hold their form. Once dried and set, the trays exit the tunnel and enter the demolding station, where the candies are gently shaken and lifted out of their starch beds. The residual starch is brushed or blown off using filtered air. At this stage, the candies are fully formed but still lack their distinctive sour coating. Their surface is slightly tacky, perfect for what comes next. The freshly demolded candies travel via belt conveyors into the tumbling drums, where the signature sour sugar coating is applied. This process is more than just dusting. It's a tightly engineered flavor delivery system. A combination of granulated sugar and food-grade acids, citric, tartaric, and sometimes fumaric, is pre-blended in exact ratios. The blend is fine-tuned to ensure that the initial bite delivers an immediate sour punch, followed by the familiar fruity sweetness that defines the Sour Patch experience. The tumbling drums slowly rotate, keeping the candies in constant motion while the sour sugar is applied. Electrostatic charge may be used to enhance adhesion, and a fine mist of water or glucose solution may be sprayed to ensure the sugar sticks evenly. The acidity level must be monitored carefully. Too much acid and the sugar may begin to dissolve or create clumps. Too little and the product loses its sour identity. Once coated, the candies are transferred to a brief curing line or rest belt, where they are allowed to stabilize. This short cooling or drying step prevents the candies from sticking together in the next stage, sizing and quality control. Here, the candies pass under a series of high-speed sensors and cameras that scan for defects. Candies that are misshaped, uncoated, or outside the standard weight range are rejected by air jets or diverting arms. A metal detector and sometimes an X-ray unit also check for foreign materials, ensuring every batch meets food safety requirements. From there, the perfect Sour Patch Kids are funneled into multi-head weighers. These machines calculate exact batch weights using multiple mini-scale heads, which work together to fill each package with consistent amounts. Whether it's a 2 Aussies snack pack or a 14 Aussies share bag, the system is tuned to deliver the exact target weight, minimizing product giveaway and packaging errors. The weighed candies drop into vertical form-fill-seal machines, where pre-printed plastic films are formed into pouches, filled and sealed at a rate of hundreds per minute. Heat-sealing jaws press the top and bottom of each bag to form a tamper-proof seal. At the same time, inkjet printers apply date codes, lot numbers, and traceability information onto the packaging. Finished pouches are conveyed to cartoning machines, which group the units into retail-ready cases or shelf displays. These cases are then stacked by robotic palletizers onto wooden or plastic pallets, stretch-wrapped for stability, and labeled with barcode and shipping information. Pallets are moved to climate-controlled warehouses where inventory is managed using first-in, first-out protocols to ensure freshness and consistency. But even before the products leave the facility, an extensive quality assurance process takes place. In on-site labs, technicians sample batches from every production shift. They test texture, moisture content, pH levels, and sour intensity using sensory panels and instrumentation. Texture analyzers simulate the bite, while gas chromatography may be used to verify flavor profiles. Sensory evaluations compare each batch to a control sample, ensuring consistency across time, shifts, and factories. Throughout the factory, automated systems tie it all together. Programmable logic controllers regulate syrup cookers, starch bed alignment, depositor temperatures, drying tunnel airflow, and coating drum speed. Human-machine interface touchscreens let operators monitor system health, while plant-wide SCADA systems log every parameter, creating a digital record that can be accessed during audits or for continuous improvement. Hygiene is also paramount. Sour Patch Kids plants are divided into sanitation zones. Wet cleaning and dry cleaning schedules rotate daily, and allergen control systems prevent cross-contamination. Starch handling areas are equipped with dust extraction systems, and gelatin systems are heat sterilized regularly. All employees wear protective clothing, and product contact zones are made from stainless steel and food-safe plastics. Sustainability is playing a bigger role as well. Waste heat from candy cookers is often recaptured to warm air for drying tunnels. Cooling water is recirculated through chillers. Packaging materials are being redesigned for recyclability, and off-spec products are diverted to animal feed or fermentation-based disposal systems. From starch beds to sugar bins, from sour spray drums to robotic sealers, every Sour Patch Kid is the product of dozens of synchronized systems working at once. Each one delivers a tiny, punchy burst of flavor and texture. But that simple experience hides a deeply engineered process. It's this contrast between playful and technical that defines the candy industry at its best. Behind the bright colors and silly branding is an intricate web of food chemistry, machine timing, thermal engineering, and human expertise. And thanks to this hidden complexity, we get a treat that's soft, sour, sweet, and unforgettable every single time. At the heart of Starburst production is its base, a cooked blend of sugar, corn syrup, and hydrogenated oil, mixed with fruit flavors, acids, and food-grade colorings. The process starts in the raw materials warehouse, where granulated sugar and corn syrup are received in bulk tankers and stored in large stainless steel silos. Hydrogenated palm or coconut oil, used to give Starburst its soft, non-sticky texture, is stored in heated tanks to keep it fluid. The first major step is preparing the candy mass, which begins in the cooking vessels. These are massive stainless steel vacuum cookers or steam-jacketed kettles. Sugar and corn syrup are metered into the vessel in precise ratios, usually around 55% sugar to 45% syrup by weight. This combination is heated gradually, first to dissolve the sugar and then to boil the mixture. Cooking temperatures generally range from 120 degrees to 130 degrees, high enough to concentrate the sugars but not so hot as to cause caramelization. To control the texture of the final product, hydrogenated oil is added partway through the process. This ingredient ensures that the candy retains its signature chewiness, resists sticking to wrappers, and holds its shape even in warm climates. The mixture is then subjected to vacuum evaporation, which rapidly reduces the water content to just a few percent. This gives the candy its dense, chewy consistency while preserving flavor compounds that would otherwise degrade at high temperatures. At this stage, the candy mass is still a blank canvas, sweet, soft, and sticky, but without any of Starburst's fruity character. That comes next, during the flavoring and coloring phase. The cooked mass is transferred to a mixing table or planetary mixer, where it is divided into batches, each destined to become a different flavor: cherry red, lemon yellow, orange, and pink strawberry. While the candy is still warm and malleable, flavorings are added using high shear mixing blades. Flavor oils, such as natural fruit esters, concentrated juices, and aroma compounds, are blended in specific ratios for each variety. Alongside these, food-grade colorants are introduced to match the flavor's visual identity. For example, a strawberry batch will receive red coloring, while lemon is paired with yellow dyes. Because flavor and color must be evenly distributed throughout the dense candy, industrial kneading machines, or two-roll mills, are used to fold the additives into the candy mass thoroughly. Once flavored and colored, the candy is allowed to cool slightly, then shaped into thick, rectangular slabs. These slabs are sent into extrusion machines, where the mass is pushed through die openings to form long, continuous ropes of Starburst candy. These ropes have a square cross-section and are designed to match the exact dimensions of the final wrapped piece. Temperature and pressure are tightly regulated during extrusion to prevent air pockets or cracking in the candy. As the ropes exit the extruder, they move through chilling tunnels, cooling conveyors that reduce the temperature of the candy from around 90 degrees Celsius down to ambient, typically 20 to 25 degrees Celsius. Chilling is critical for maintaining clean cuts during the next step, forming and cutting. Once fully cooled and firm, rotary guillotine blades or high-speed slicers cut the ropes into individual squares, each weighing approximately 5 to 6 grams. Timing must be exact. Too soon, and the candy may deform. Too late, and the blades will struggle to penetrate the firm mass. With the individual Starburst pieces formed, attention shifts to wrapping. And this is where one of the most recognizable elements of the brand, the folded wax paper wrapper, comes into play. Unlike most candies that are flow-wrapped in plastic, Starburst pieces are wrapped in waxed paper for a nostalgic, premium feel. Specialized fold wrapping machines wrap each candy in a continuous paper feed, cutting and folding the paper tightly around each piece. These machines operate at incredible speeds, typically wrapping hundreds of pieces per minute per lane. The wrapper is folded around the candy in a precise sequence, first lengthwise, then tucked on both ends, and finally pressed to seal. Heat is not used here. Instead, the pressure of the folding mechanism and the wax's natural tackiness create a secure seal. The wrapped pieces are then grouped into multi-packs, usually 4 per stick, and banded with a printed paper sleeve. The packaging process continues on another line, where multi-packs are fed into cartoning machines. These machines stack individual 4-packs into larger display boxes or retail cartons, often 12, 24, or even 36 per case, depending on distribution needs. Robotic case packers load the cartons into corrugated master cases, which are then palletized, stretch-wrapped, and labeled for shipping. Before shipping, however, Starburst undergoes a battery of quality control tests. Throughout the line, samples are pulled to ensure that texture, flavor, size, and wrapper adhesion all meet specification. In the QA lab, texture analyzers measure the chew resistance and flexibility of each batch, while colorimeters assess hue accuracy for visual consistency. Trained sensory panelists sample each flavor, comparing it to gold standard references from previous batches. These tastings are essential for detecting any subtle shifts in flavor due to ingredient variability or equipment drift. Food safety is equally critical. Metal detectors and X-ray scanners are placed on the line just after the wrapping stage, scanning every piece or group for foreign material. Any flagged product is immediately removed from the stream and investigated. Allergen control systems are in place to segregate any shared lines, especially if seasonal or limited edition flavors introduce dairy or nut-derived ingredients. Plant operations are governed by integrated SCADA and PLC systems that automate and monitor every major step, from syrup cooking temperatures to extrusion belt speeds, wrapping line tension, and packing efficiency. These systems not only reduce labor and error, but also capture critical data for traceability. Every batch can be traced back to its ingredient lot, cooking time, and packaging line, an essential feature in today's tightly regulated food environment. From a sanitation standpoint, Starburst production is a model of modern food safety. The equipment is built for easy disassembly and frequent cleaning. Clean-in-place systems flush cooking tanks, while manual cleaning crews address extruder heads, knives, and wrappers during line changeovers. Air handling systems maintain positive pressure in the production area to reduce contamination risk from outside environments. The flavor development behind Starburst is equally fascinating. Before a flavor ever reaches the line, it's tested in pilot plants, small-scale versions of the main facility where new formulations are trialed for chew, shelf life, and stability. Flavor chemists work to balance the punchy fruit notes with the candy's base, sweetness, and acidity. The chew is critical too. It must start firm but give way without sticking to teeth. Achieving that requires just the right combination of sugars, fats, and starches, all of which are adjusted slightly for each formula. Starburst production also involves strategic international planning. While many factories produce core flavors, special editions, like tropical or sour varieties, may be manufactured in dedicated facilities optimized for unique formulations. These versions often include additional steps, such as surface sour sanding or multicolor striping, adding to the production complexity. On the sustainability front, some factories now source RSPO certified palm oil and use high-efficiency boilers to reduce energy consumption. Waste heat from the cooking line is sometimes reused for water heating or dehumidification. Candy offcuts and miswraps, when safe and hygienic, are often reground and reprocessed into new batches, keeping waste to a minimum. In total, a single Starburst square may take over 24 hours to go from raw syrup to final wrapped piece. And yet, thanks to the scale and precision of modern automation, millions of these squares are produced each day, each one perfectly formed, brightly wrapped, and bursting with flavor. What seems like a simple treat is, in reality, the product of dozens of coordinated systems: syrup chemistry, extrusion dynamics, flavor infusion, robotic wrapping, quality assurance, and logistics. From the chewy texture to the tangy flavor and satisfying unwrapping ritual, Starburst delivers a sensory experience that's engineered from the ground up. So the next time you unwrap that bright pink square and let it slowly melt in your mouth, remember, behind that single bite lies an entire factory's worth of work, creativity, and technical mastery, designed not just to make candy, but to make joy. In a modern Oreo manufacturing facility, key dry ingredients are delivered in bulk, often by rail cars or food-grade trucks, and are pneumatically conveyed into large storage silos made of stainless steel or epoxy-lined carbon steel. These silos are sealed from air and moisture and are connected to the factory's central control system. The main dry ingredients include unbleached, enriched wheat flour, processed cocoa powder, granulated sugar, and minor dry components like baking soda and salt. Each of these materials is handled in its own silo or hopper, and automated augers or vibratory feeders dispense precise quantities into batch weighing hoppers. These hoppers sit on load cells, sensitive scales that can measure down to a fraction of a gram. This is essential because the correct ratio of flour to cocoa to sugar directly affects not only the flavor, but also how the dough behaves under pressure during molding. If the cocoa content is even slightly too high, for instance, the dough may become too brittle and crack during forming. If it's too low, the wafers may bake up too soft, losing the crisp snap that defines an Oreo. Once the dry materials are batched, they are conveyed into a pre-mixing chamber. At this stage, powdered ingredients are briefly tumbled together to ensure initial homogeneity before liquids are added. Then it's time for the liquid components to enter the system. These include vegetable shortening, often a blend of palm and canola oil, along with a sugar syrup or glucose solution, invert sugar, lecithin, and vanillin or other flavoring agents. The fats and liquids are stored in temperature-controlled tanks and are metered into the mixer through heated pipes. The temperature of the fats is critical. Too cold, and they won't disperse evenly. Too hot, and they could melt too aggressively, breaking down the emulsion and affecting dough integrity. All of these components are combined in large jacketed horizontal mixers or double sigma arm batch mixers. These mixers are chosen for their ability to handle heavy, cohesive doughs while still ensuring thorough dispersion. Inside the mixer, paddles or blades knead the dough continuously, folding and stretching it to develop a uniform texture. The mixer operates under a specific time and speed profile, starting slow to incorporate the dry and wet components, then increasing speed to blend, then finishing with a gentle knead to avoid overworking the dough. The goal here is a dough that's soft but not sticky, cohesive but not tough. Sensors inside the mixing chamber monitor temperature and torque, two key indicators of dough readiness. If the dough becomes too warm from friction, it can become greasy and difficult to form clean edges in the molding machines. If it's undermixed, the ingredients won't be uniformly distributed, and inconsistencies in cookie size, color, and bake profile will result later on. Once the dough reaches its target specifications, it's discharged from the mixer through a hydraulically controlled trapdoor at the base of the mixing tank. The dough falls into a dough transport system, typically a set of conveyors or troughs lined with non-stick materials like Teflon or food-grade UHMW polyethylene. At this stage, the dough may still be slightly warm, around 30 degrees Celsius to 35 degrees Celsius, and has a dense, matte appearance with a strong cocoa aroma. Before moving to the forming machines, the dough must undergo a resting period in certain operations. This allows the flour to fully hydrate and any residual gases or trapped air to escape. In high-speed production environments, however, this rest period may be minimized or skipped altogether if the formulation is optimized for immediate processing. This completes the initial phase: ingredient intake, formulation, mixing, and dough discharge. Each step up to this point is carefully controlled by recipe management software that ensures no human error can affect batch consistency. Recipe locks, scanner-based operator identification, and redundant scale verification ensure each batch of Oreo wafer dough is made precisely to the specifications required to perform flawlessly in the next stage of the journey, shaping and embossing. Now that the chocolate wafer dough has been prepared with absolute precision, measured, mixed, and conditioned, it moves into one of the most visually iconic and mechanically fascinating phases in the Oreo production line, forming and molding. This step takes the dense, cocoa-rich dough and transforms it into thousands of uniformly sized, detailed cookie wafers, each embossed with the distinctive Oreo pattern. This is not simply cutting shapes out of dough, it's a highly engineered, high-speed process where consistency in shape, thickness, and surface detail must be maintained across millions of units every day. The freshly prepared dough is conveyed to a hopper positioned above a sheeter. This sheeter is a wide, stainless steel roller assembly that flattens the dough into a uniform sheet of specific thickness. The dough moves between a set of rollers, typically 2 or more steel cylinders calibrated to exact tolerances that compress it to the target height. For Oreo wafers, the final sheet is quite thin, often around 3 to 4 millimeters, with a consistent density and moisture distribution. Getting this thickness right is critical. If the sheet is too thick, the cookie may not bake evenly or could become too brittle. Too thin, and the cookies may crack, burn, or crumble during sandwiching. Sensors measure the thickness of the sheet continuously using laser or ultrasonic gauges. If deviations are detected, servo-driven actuators automatically adjust roller spacing to maintain precision. The sheeter also includes edge trimmers, small, motorized blades that cut off uneven or frayed edges of the dough sheet to keep the line uniform. The trimmed edges are collected by a scrap recovery system and reintroduced into the mixing system, minimizing waste without compromising freshness or quality. Once the dough sheet is perfected, it enters the rotary molder. This machine is central to the Oreo brand's identity, as it forms the shape, size, and embossed design of each cookie wafer. The rotary molder consists of 2 primary components, a rotating die roller and a pressure roller. The die roller is a cylindrical drum engraved with multiple cavities, each one precisely carved with the Oreo design. These cavities aren't just cosmetic. Their depth and contour dictate the final relief of the cookie surface. As the dough sheet passes between the die roller and pressure roller, each cavity punches into the dough, compressing it into shape and imprinting the Oreo design. The pressure roller, covered in food-safe rubber or polymer, pushes the dough up into the die cavities, ensuring a clean, complete mold. As the die drum continues rotating, the shaped wafers are extracted by a combination of mechanical pushes and vacuum assist systems, which gently remove the cookies from the cavities without smudging the design. These freshly molded cookie wafers are then transferred onto a wide mesh conveyor belt in a continuous, uninterrupted line. Each wafer is spaced evenly to allow for proper airflow in the next phase, baking. Meanwhile, the excess dough surrounding the cutouts, known as webbing, is carefully separated and sent back through the scrap system. This recovery loop is highly efficient, capturing nearly 100% of the unused dough and returning it to the mixer via chilled transport belts. To ensure product consistency, reworked dough is blended at a fixed percentage into fresh dough, preventing any changes in texture, flavor, or moisture that might result from overprocessing. As the line of uniform, molded Oreo wafers advances, they approach the baking tunnel, one of the most thermodynamically sophisticated parts of the facility. The tunnel oven is a massive structure, often exceeding 30 meters in length, segmented into multiple temperature-controlled zones. Each zone is precisely tuned to manage the gradual dehydration and expansion of the cookie, ensuring even baking from edge to center. The ovens use convection, conduction, and in some cases, radiant heat, depending on the equipment manufacturer and regional factory specifications. The cookie wafers bake as they travel slowly through the tunnel, typically for a duration of 4 to 6 minutes. Conveyor speed, airflow rate, and internal oven temperatures are continuously adjusted via programmable logic controllers that interface with sensors monitoring internal humidity, surface temperature, and even color of the baking cookies using infrared imaging systems. The target bake is one where the cookie becomes crisp and fully set while retaining a slight moisture gradient at its core, enough to ensure it sandwiches cleanly without shattering, and holds up in milk without becoming soggy too quickly. Another crucial parameter monitored at this stage is cookie spread and diameter. Because the molded wafers expand slightly as they bake, their final size must fall within a fraction of a millimeter to ensure they'll match perfectly with their paired half during sandwiching. Edge blowout, where cookies develop uneven bulges or bubbles, is prevented by careful control of initial dough temperature, mold compression depth, and oven humidity during the first baking phase. As the cookies exit the oven, they are immediately passed through a staged cooling system. This phase is designed to gently bring the cookies from their internal post-bake temperature of roughly 160 degrees Celsius down to ambient room temperature. Cooling too quickly can cause the wafers to crack, warp, or experience checking, tiny surface fractures that affect aesthetics and structural integrity. To avoid this, the conveyor slowly moves the wafers through a series of cooling zones with progressively decreasing airflow temperatures. High-volume fans push filtered, dehumidified air over the wafers in a cross-flow pattern that cools them evenly on all sides. By the time the wafers reach the end of the cooling tunnel, they are firm, crisp, and at a stable moisture level, typically around 1.5% to 2%. This ensures maximum shelf life, a satisfying crunch, and ideal compatibility with the creme filling in the next phase of production. They are now ready for alignment and pairing. Wafers are automatically aligned into dual streams using diverters and channeling guides. Conveyor belts equipped with vision systems scan for defects such as missing embossing, chips, discoloration, or breakage. These systems use high-speed cameras and AI-assisted pattern recognition to detect any imperfections in milliseconds. Rejected cookies are diverted to a waste collection hopper, and approved wafers continue forward to the sandwiching stage. With the Oreo chocolate wafer cookies fully formed, baked, and cooled, the production line now transitions into one of the most iconic and mechanically synchronized parts of the process: sandwiching. This stage involves the precise alignment of two delicate wafer halves around a carefully deposited swirl of creme filling, forming the complete Oreo cookie as we know it. What may seem like a simple task, placing filling between two cookies, is in fact a highly controlled and technically advanced process that prioritizes speed, accuracy, hygiene, and product consistency. The cooled wafers arrive at the sandwiching station via dual-lane conveyors that separate and feed cookies into two different orientations: bottom wafers and top wafers. The bottom wafers are destined to receive the cream filling, while the top wafers are held back momentarily, synchronized to arrive just as the filling has been deposited. Vision-guided pick-and-place arms or mechanical guides ensure that each cookie is properly positioned and oriented with the embossed design facing upward, especially important for branded recognition in the final presentation. The placement needs to be exact. Even a slight misalignment could result in uneven sandwiching or a crooked creme center, which would be rejected downstream. At the heart of the sandwiching line is the creme depositor. This component is engineered to dispense a precise amount of creme onto the center of each bottom wafer. The creme filling itself has been prepared earlier in the process and is stored in stainless steel holding tanks near the sandwiching line. The base creme is a blend of vegetable shortening, powdered sugar, and natural or artificial flavorings, aerated to achieve a smooth and creamy texture. It is kept at a controlled temperature, typically between 25 degrees Celsius and 30 degrees Celsius, to maintain flow consistency without being too runny or too firm. The creme is pumped into the depositor through a jacketed delivery line, which maintains temperature and prevents any hardening or separation. Inside the depositor, a rotary valve system or piston-driven nozzles release measured quantities of filling in circular swirls directly onto each passing wafer. The target deposition amount is extremely precise, usually around 3 grams per cookie for the original Oreo. For double stuff, the system is calibrated to deliver twice that volume, and the depositor nozzle height is adjusted accordingly to accommodate the larger swirl. The deposition speed is synchronized with the conveyor, meaning each swirl is deposited while the bottom wafer is in motion. To maintain consistent swirl shapes, the nozzle spins at a high RPM as it dispenses the cream. Sensors and imaging software track swirl size, height, and position. If the deposit strays from the central zone or falls outside weight tolerances, that cookie is automatically flagged and diverted. These sensors run continuously, sampling thousands of cookies per minute with extremely tight thresholds for variance. Once the creme is in place, the top wafer is gently placed onto the swirl. This is done by an overhead transfer arm or drop chute designed to lower each top cookie into place with just enough pressure to make contact without squashing the filling. The timing here is critical. Placing the top wafer too early could create smearing or incomplete adhesion, while placing it too late could allow the creme to set and result in a loosely held sandwich. Once the two halves make contact, a calibrated compression roller or paddle gently presses them together to create a uniform sandwich with a visible, even creme edge. The newly assembled Oreo cookies are then conveyed forward to undergo another round of quality inspection. At this stage, high-speed vision systems again scan for defects. These include cracked or broken wafers, misaligned sandwiches, off-center cream, or excess filling that has oozed out past the edges. Cookies that fail to meet standards are ejected via pneumatic pushers or retractable gates, landing in separate bins for non-conforming product. These rejected cookies are either discarded or recycled depending on factory policies and whether they passed earlier food safety checks. The good cookies move on to the next major phase, cooling and setting. Even though the creme filling is solid at room temperature, the act of depositing and sandwiching generates residual warmth, and the filling remains somewhat malleable for several minutes. To stabilize the sandwich structure and ensure long-term integrity during packaging and shipping, the cookies are passed through a controlled cooling tunnel. This tunnel gradually brings the product's temperature down to a stable point, typically just below ambient, which firms up the cream and locks in the sandwich's structural cohesion. As cookies exit the cooling tunnel, they are directed toward the packaging line. Here, the cookies are grouped and arranged into stacks or rows depending on the intended package format, whether it's a classic tray-style retail pack, a resealable pouch, a single-serving sleeve, or a multi-pack unit. For traditional packs, the cookies are guided into channels that group them into stacks, typically of 3 or more, which are then lowered into thermoformed plastic trays by robotic pick-and-place units. These trays help protect the cookies from damage and keep them organized for end-user convenience. Parallel to this, packaging film, pre-printed with branding, nutritional labels, and product information, is unwound from large rolls and fed into a form-fill seal machine. As the cookie-filled trays pass through the machine, the film is wrapped around the product, heat-sealed on all sides, and trimmed to size. Oxygen scavengers or desiccants may be inserted for freshness in some markets, depending on climate and shelf life requirements. For resealable packs, a Ziploc or peel-back adhesive strip is applied as part of the film sealing process, ensuring that consumers can open and close the package without reducing freshness. Each package unit is printed with a lot number, manufacturing date, facility code, and expiration date using high-speed thermal inkjet or laser printers. These codes enable full traceability and are cross-referenced with the production batch data stored in the factory's ERP system. From mixing and molding to creme filling and sealing, every step of the process can be traced back to specific machines, operators, shift schedules, and ingredient batches, an essential feature for food safety compliance and recall readiness. Once sealed, packages are conveyed to automated case packers. Here, robotic arms load the wrapped units into corrugated cardboard cartons, which are then glued or taped shut. These cartons are palletized according to preset patterns that optimize load stability and cube efficiency for shipping. Pallets are wrapped with stretch film, labeled with shipping barcodes and inventory data, and routed to the warehouse staging area. At this point, the Oreo cookies have completed their physical transformation from separate cocoa wafers and creme filling into a polished, fully packaged, ready-to-ship product. But before they leave the factory, they undergo a final quality audit. Samples from each batch are pulled from the finished goods line and tested by in-house sensory panels and laboratory staff. Taste, texture, aroma, appearance, and moisture content are evaluated to ensure that the product not only looks perfect, but delivers the consistent flavor and mouthfeel that Oreo is known for. Moisture levels are especially critical. Too high, and the cookie can lose its crispness during storage. Too low, and it can become brittle or stale. Texture analyzers apply mechanical pressure to the cookies to evaluate crunch resistance and breaking force, while gas chromatography is used to verify flavor compound profiles. Packaging integrity tests include drop tests, seal strength verification, and temperature cycling simulations that mimic transport and storage conditions across various markets. Once these final inspections are passed, the cookies are released for distribution. Pallets are loaded into climate-controlled trucks or containers, routed through regional distribution centers, and ultimately arrive at retail outlets, vending networks, or direct-to-consumer channels. With the Oreo cookie now fully assembled, inspected, packaged, and palletized, the final phase of the in-factory process is dedicated to the logistics, storage, inventory control, and outbound quality assurance systems that prepare the product for global distribution. While it may seem like the technical complexity is behind us, this stage involves its own set of sophisticated workflows designed to ensure that every package remains pristine, traceable, and shelf-stable for months after production, regardless of whether it ends up in a small, rural convenience store or a high-volume urban supermarket. The finished pallets of Oreos are moved from the end-of-line palletizing systems into a dedicated finished goods warehouse. This space is part of the factory complex, but isolated from production to prevent cross-contamination and maintain temperature and humidity stability. Oreo cookies, especially those with creme fillings, are highly sensitive to environmental changes. Excessive heat can soften the filling or compromise the packaging seal, while high humidity can cause moisture migration into the wafer, leading to loss of crispness. To combat these risks, the warehouse is maintained at a tightly regulated temperature, typically between 18 degrees Celsius and 22 degrees Celsius, with relative humidity kept under 50%. The facility is segmented into climate zones for different packaging formats, with certain areas reserved for international shipments that may require added humidity resistance or longer storage durations. Air handlers, industrial-grade dehumidifiers, and air filtration systems constantly regulate and cycle the air to maintain these parameters. Even the lighting systems are designed to minimize UV exposure, which could, over time, degrade packaging ink or food contact films. Once inside the warehouse, each pallet is scanned and logged into a warehouse management system. This system is fully integrated with the factory's enterprise resource planning software and allows operators to track, Not only where each pallet is stored, but exactly what production line, time, and ingredient lot was used to produce its contents. Each pallet label includes a unique serial number, barcode, and QR code that links to this full production history. This traceability is essential not just for internal logistics, but also for compliance with food safety regulations around the world, which require manufacturers to be able to track every product from raw ingredient to final point of sale. The WMS automatically arranges pallets by product type, batch date, and destination. Those scheduled for export may be routed to a separate staging zone where they will be checked for compliance with international packaging laws. Different markets may require translated labels, adjusted nutritional formats, or modified lot codes. Some export destinations also require additional tests, such as microbial swabs or accelerated shelf life sampling, to meet foreign government regulations. These are performed in an adjacent quality control annex, and only upon clearance are these pallets released to outbound logistics. Before any Oreo shipment leaves the facility, it undergoes a final visual inspection for physical damage to packaging, tamper seals, and box integrity. Any visible damage may indicate mishandling during internal transit or weak spots in pallet stability. Operators are trained to look for warped trays, compromised seals, or even small tears in the flow wrap film that could affect product freshness. Should any defect be discovered, that pallet is held for secondary inspection, and depending on severity, it may be repackaged or scrapped entirely. At this point, logistics coordinators use automated routing systems to schedule outbound shipments. These systems factor in geographic location, delivery deadlines, climate conditions, and truck availability. For example, shipments bound for warmer climates during the summer may be prioritized for insulated or refrigerated trucks to prevent the creme from softening. Long-haul shipments may be routed through distribution centers that offer cross-docking or climate-controlled storage to preserve product quality along the supply chain. The loading dock itself is operated with precision. Trucks arriving at the facility must be cleaned, inspected, and approved before any Oreo products are loaded. This includes visual inspection for pests, residue from prior shipments, and confirmation that the trailer temperature is within specification. Only after a truck passes these inspections does the facility open the dock door and begin the loading sequence. Robotic forklifts or human operators load the pallets according to pre-planned diagrams that ensure weight is evenly distributed and product is easily accessible at the destination. Each shipment is logged with time, driver ID, carrier information, route ID, and estimated delivery window. Once loaded, trucks are sealed with tamper-evident locks and dispatched with digital shipping documents, including delivery confirmations and scanned QR codes for receiving teams. The WMS updates the ERP system in real time, closing the inventory loop and marking the batch as shipped. This inventory and logistics traceability is crucial for meeting compliance with global food safety standards like the Global Food Safety Initiative, hazard analysis, and critical control points, and ISO 22000. Even after the Oreo product leaves the plant, the factory remains connected to its life cycle through digital feedback systems. Retailers and distributors have access to portal-based interfaces where they can report damages, delayed deliveries, or unexpected inventory issues. Returned products are scanned upon arrival at reverse logistics zones where factory staff investigate issues, analyze production records, and determine root causes. In cases where errors are found, such as premature staleness, flavor imbalance, or packaging failure, continuous improvement protocols are triggered to address the upstream causes. While these systems function to protect the product, they also feed into a broader factory goal: performance analytics and continuous optimization. The data from every shipment, temperature logs, shipping duration, breakage rates, seal integrity, and even consumer complaints is compiled into dashboards reviewed weekly by production leads, QA managers, and logistics coordinators. These dashboards enable the factory team to track KPIs like OTIF, defect per million rates, inventory turnover, spoilage reduction, and carbon footprint per pallet. Some Oreo plants are moving even further towards sustainability at this stage of production. Cardboard shipping boxes are made with recycled content and are themselves fully recyclable. Pallet wrap films are being downgauged or replaced with biodegradable alternatives. Facilities are experimenting with hybrid electric fleet partnerships or rail transport instead of trucks to reduce emissions. In select markets, even the plastic trays inside Oreo packs have been redesigned for recyclability, and clear labels now inform consumers on proper disposal. Hershey's chocolate production begins with the arrival of raw cocoa beans at its manufacturing plants, most notably in Hershey, Pennsylvania, where some of the largest scale chocolate operations in North America take place. These beans are imported from cocoa-producing regions around the equator, including West Africa and parts of Central and South America. Upon arrival, the beans are offloaded into receiving silos and moved into the first processing step: cleaning. Powerful vibrating screens, aspirators, and magnetic separators remove debris, stones, twigs, dust, and any metallic fragments that may have entered the shipment during transit. Following cleaning, the cocoa beans are fed into Hershey's proprietary roasting system. The roasting process is designed not just to sterilize the beans, but to precisely control flavor development. The machines are capable of adjusting roast temperature, humidity, and dwell time based on the origin, size, and moisture content of each batch. Beans are typically roasted at temperatures ranging from 120 to 160 degrees Celsius. This is where the characteristic chocolate aroma begins to develop, as volatile compounds are released and the Maillard reaction activates, producing hundreds of unique flavor notes that define Hershey's mild, sweet chocolate style. After roasting, the beans are cooled and moved to the winnowing section, where they are cracked open and the outer shells are separated from the valuable inner nibs. Winnowing is accomplished using a combination of mechanical cracking and airflow separation. The shells, now removed, are often collected and repurposed as agricultural mulch or biomass fuel. The nibs, the true essence of chocolate, contain both cocoa butter and cocoa solids, and are now ready for the next phase: grinding. The nibs are fed into high-capacity industrial grinding mills, where intense mechanical shear forces break down the cellular structure and release the natural cocoa butter, forming a dense, fluid paste known as chocolate liquor. Despite its name, chocolate liquor contains no alcohol. This liquor is a pure, unsweetened, dark brown substance composed entirely of finely ground cocoa particles suspended in cocoa butter. From here, the liquor may go into temporary holding tanks or be immediately sent to blending tanks, depending on product demand. To make Hershey's classic milk chocolate, the chocolate liquor is blended with sugar, milk derivatives, cocoa butter, and small amounts of flavoring agents and emulsifiers. What makes Hershey's process unique is its use of fresh milk, originally pioneered by Milton Hershey himself, which is condensed and cooked on site. This milk is blended with sugar and chocolate liquor to form a slurry, which is then dried into what's known as milk crumb. The milk crumb is one of the keys to Hershey's signature, tangy, almost caramelized chocolate flavor. Unlike many European chocolate makers who use dry milk powders, Hershey's milk crumb production adds distinctive cooked dairy notes that have become synonymous with the brand's taste. The crumb mixture is then blended with additional chocolate liquor and cocoa butter in massive mixers to create a semi-fluid chocolate paste. This paste now contains all of the major components of Hershey's chocolate: milk solids, sugar, cocoa mass, and cocoa butter. However, it still needs to be refined to achieve the ultra-smooth texture that consumers expect. This refinement is achieved using a 5-roll mill, a piece of precision equipment where the chocolate paste is passed through a series of steel rollers that reduce particle size down to around 15 to 20 microns, small enough that the human tongue can no longer detect individual sugar or cocoa particles. Following refining, the chocolate mixture is fed into conchis, large horizontal vessels fitted with heavy-duty rotating arms. Conching is both a mechanical and thermal process in which chocolate is kneaded and aerated for several hours at controlled temperatures. During this stage, volatile acids are evaporated, off flavors are reduced, and cocoa solids become fully coated in cocoa butter, resulting in a more uniform flavor and mouthfeel. Hershey's conching times and temperatures are tightly guarded trade secrets, but generally range between 3 to 12 hours, depending on the chocolate type. Once conching is complete, emulsifiers like soy lecithin or PGPR may be added to improve flow characteristics and ensure the chocolate performs consistently during molding and enrobing. The now finished chocolate is transferred into tempering machines, where it is carefully cooled and reheated to stabilize the crystalline structure of the cocoa butter. Proper tempering is crucial to ensure the finished chocolate will have a glossy appearance, a sharp snap when broken, and resistance to fat bloom. Tempered chocolate is then routed to forming lines. For products like Hershey's milk chocolate bars or Hershey's Kisses, high-speed molding machines deposit the liquid chocolate into custom molds. These molds are vibrated to eliminate air bubbles and achieve uniform density before passing through long cooling tunnels. As the chocolate cools and solidifies, it contracts slightly and is released cleanly from the molds onto conveyors, ready for wrapping. Each chocolate piece is visually inspected, sometimes using high-speed cameras and vision systems, to ensure correct shape and fill. Hershey's Kisses, for example, go through dedicated foil wrapping machines that not only wrap each piece in branded foil, but also insert the iconic paper plume. Bars are fed into flow wrappers that apply sealed plastic or foil film, printed with lot numbers and expiration dates for traceability. From there, wrapped products are packed into cartons, sealed, labeled, and automatically palletized. Finished pallets are stored in climate-controlled warehouses maintained at stable temperatures and humidity to preserve texture, flavor, and appearance. Before any product is shipped out, samples from each production batch are tested in Hershey's quality control labs. There, technicians measure viscosity, particle size, pH, and fat content, and perform sensory evaluations to confirm that every batch meets the company's rigid standards for flavor and mouthfeel. Snickers, one of the most iconic candy bars in the world, is produced through a multi-stage industrial process that combines confectionery precision, mechanical engineering, and high-speed automation to create its distinctive layers of nougat, caramel, peanuts, and chocolate. Every bar must deliver the exact same ratio of texture and flavor, whether it's made in a facility in the United States, Europe, or Asia. With millions of bars produced daily, the manufacturing of Snickers is a tightly controlled operation with specific systems dedicated to each layer of the bar, all integrated into a seamless production line that ensures uniformity, food safety, and efficiency. From raw ingredient handling to final packaging, the Snickers factory operates with synchronized precision. Production begins with the preparation of the nougat layer, which forms the foundational base of every Snickers bar. The nougat used in Snickers is a whipped, chewy confection made from a combination of sugar, corn syrup, egg whites, milk powder, cocoa, and a small amount of salt. These ingredients are first loaded into industrial mixing vessels where they are cooked and then aerated. The sugar and corn syrup are heated together in a jacketed kettle until they reach a temperature between 115 degrees Celsius and 125 degrees Celsius. This heating process is tightly controlled through automated sensors that ensure consistent viscosity and prevent burning or crystallization. Once the syrup mixture reaches the desired temperature, it is transferred into a high-capacity continuous mixer, where egg whites and milk powder are added. Compressed air or nitrogen gas is also injected to whip the mixture into a soft, foamy texture. This aeration step is critical. It gives the nougat its characteristic lightness and chewiness. The temperature, gas pressure, and mixing speed are all precisely monitored by programmable logic controllers, which adjust the input in real time to maintain consistent product density and texture. The aerated nougat is then deposited as a thick slab onto a moving conveyor belt. This belt passes through a cooling tunnel that gradually reduces the temperature of the nougat slab to stabilize its structure. The cooling tunnel is divided into zones, each maintained at a different temperature to prevent rapid contraction, which could cause cracking or uneven density. Once cooled, the nougat slab is cut longitudinally into ribbons, the exact width of a Snickers bar, and then cross-cut into bar-sized sections using high-speed guillotine knives. These knives are synchronized with the conveyor's motion to ensure clean, accurate cuts without deforming the soft nougat. Next comes the caramel layer. The caramel used in Snickers is thick and elastic, designed to stretch but not melt under room temperature. It is made from a cooked blend of glucose syrup, sugar, milk solids, butterfat, and a carefully calibrated emulsifier. The cooking process begins in a steam-jacketed cooker, where the ingredients are brought up to approximately 118 degrees Celsius. The precise cooking temperature ensures the right balance between chewiness and flow. Overcooked caramel would become brittle, while undercooked caramel could seep through the nougat or ooze during packaging. Once cooked, the caramel is pumped into a depositor system that lays a continuous sheet of caramel over the cooled nougat ribbons. This depositor uses pressurized nozzles that spread the caramel evenly across the top surface of the nougat. The caramel is still warm and pliable at this point, allowing it to form a tight bond with the underlying layer. As the conveyor continues to move, the nougat and caramel combination enters another cooling tunnel where the caramel layer is firmed to a stable consistency. Here again, the temperature gradient is critical. The cooling must be fast enough to stop flow, but slow enough to avoid separating from the nougat base. After the caramel is stabilized, whole roasted peanuts are applied. Snickers uses high-grade peanuts that are dry roasted on-site or sourced from dedicated peanut processors. These peanuts are first cleaned, sorted, and passed through color and size grading machines. Roasting is carried out in rotary drum roasters, where temperatures are maintained around 160 degrees Celsius. After roasting, peanuts are cooled rapidly using ambient or forced chilled air to stop the cooking process and retain crunch. The cooled peanuts are then sprinkled over the still sticky caramel layer using a controlled vibratory feeder. These feeders dispense peanuts in an even distribution, and excess nuts are collected and recirculated to avoid waste. Once applied, the peanut caramel nougat stack moves through a compression station where soft rollers press the peanuts gently into the caramel to ensure adhesion. This step is essential to prevent peanuts from falling off during enrobing and packaging. The multi-layer slab is then cut again, first lengthwise into individual bar width strips, then crosswise into single units. High-speed ultrasonic knives are often used in this phase to make clean cuts through the sticky peanut caramel mass without dragging or deforming the shape of the bar. These knives vibrate at ultrasonic frequencies, reducing friction and keeping each cut smooth and precise. As with earlier cutting stages, sensors track bar dimensions, and any piece that falls outside specified tolerances is rejected automatically. Now, the cut bars are conveyed into the enrobing chamber, where they are coated with milk chocolate. The chocolate used in Snickers is a proprietary milk chocolate blend containing cocoa solids, cocoa butter, sugar, milk powder, and emulsifiers. This chocolate is kept in tempering tanks where it is heated and cooled in a controlled cycle to form stable cocoa butter crystals. Proper tempering is crucial for ensuring that the chocolate coating is glossy, has the right snap, and doesn't develop fat bloom over time. Inside the enrober, each bar passes over a fine mesh conveyor that dips the underside of the bar in chocolate. A curtain of tempered chocolate then flows over the top of each bar, fully enrobing it. Excess chocolate is removed by controlled air jets or vibrating mechanisms, which ensure a consistent coating thickness without pooling or streaking. As the chocolate sets, decorative ribbons or textures may be applied to the top surface using nozzles or air patterns. After enrobing, the bars enter the final cooling tunnel. This tunnel is typically 20 to 30 meters long and divided into multiple zones, with temperatures gradually decreasing from around 15 degrees Celsius to 5 degrees Celsius. The goal here is to allow the chocolate to crystallize into a firm, uniform shell without cracks or surface defects. Conveyor speed and cooling tunnel temperature are constantly adjusted to account for changes in factory humidity or chocolate flow rate. Once the bars exit the cooling tunnel, they move to the packaging area. Here, vision systems inspect the bars for defects, such as incomplete coating, misshapen forms, or incorrect size, and reject any units that don't meet quality standards. Accepted bars move into a high-speed flow wrapping machine. This machine dispenses printed plastic film from large rolls, forms it into a sleeve around each bar, seals the ends and back, and prints lot numbers, expiration dates, and traceability codes onto the packaging. Bars are grouped and packed into cartons automatically, then palletized using robotic arms or automatic stackers. Each pallet is labeled with its production date, factory ID, and batch number, and stored in a temperature-controlled warehouse. Finished Snickers bars are shipped daily to retailers, wholesalers, and export hubs with real-time tracking through the company's logistics and ERP systems. This ensures traceability from raw ingredient to retail shelf and allows for rapid recall or investigation if any quality issue arises in the field. Snickers production is supported by continuous quality assurance throughout every phase. From incoming raw ingredients to the final product, quality technicians perform random sampling and laboratory testing for moisture content, peanut roast quality, chocolate temper index, caramel viscosity, and microbial counts. Every component, nougat, caramel, chocolate, peanuts, is monitored to within narrow tolerances. If even a single component batch shows deviation, it can be traced, flagged, and excluded from the production cycle. In addition to quality, food safety and hygiene are rigorously maintained. All machinery is subject to clean-in-place protocols, and workers adhere to strict sanitation and allergen handling rules. Due to the presence of peanuts, dedicated production zones and air handling systems are used to prevent cross-contamination with other product lines in multi-product factories. The Snickers production process is also increasingly supported by digital technology. Smart sensors, machine learning models, and real-time analytics are used to monitor equipment performance, detect subtle variances, and suggest preventative maintenance. Digital twins of the production line can simulate different production scenarios, like ingredient substitutions or temperature fluctuations, to predict impacts before they occur in the real world. This data-driven approach allows Mars, Inc., the manufacturer of Snickers, to continuously refine and optimize its production across multiple global sites. Twix is a beloved chocolate bar recognized globally for its iconic combination of crisp biscuit, chewy caramel, and smooth milk chocolate. Its appeal lies in the precise layering and the uniformity with which each bar delivers the same balance of texture and flavor. Behind its simple appearance is a highly engineered manufacturing process that seamlessly integrates baking, confectionery science, and automated packaging on a vast industrial scale. Producing millions of Twix bars daily in factories around the world requires meticulous coordination across every step of production, from dough mixing to chocolate enrobing, all operating under strict food safety protocols and quality control systems. The following in-depth look walks through the entire process, detailing how Twix is made in a modern factory environment, step by step, with over 1,600 words devoted to the subject. The process begins with the foundation of the Twix bar, the biscuit base. This shortbread-like component is central to the signature texture of Twix, light, crunchy, and buttery without being too sweet. The ingredients for the biscuit base include wheat flour, vegetable oil or shortening, sugar, salt, and leavening agents. These raw materials are delivered to the facility in bulk, typically stored in stainless steel silos or sealed containers to protect against moisture and contamination. The dry ingredients are conveyed into high-capacity horizontal mixers, where they are combined with fats and a small amount of water. These mixers are programmed to replicate the specific time, temperature, and mixing intensity needed to create the ideal dough consistency. Overmixing is carefully avoided to prevent gluten development, which would make the biscuit tough rather than tender and crisp. The dough is monitored for temperature, moisture content, and texture using inline sensors, ensuring consistency across every batch. Once mixed, the dough is transferred to a sheeting machine. This equipment rolls the dough into a uniform sheet of precise thickness, typically between 5 to 7 millimeters, depending on the specific product variant. The sheet passes through multiple sets of rollers to ensure evenness, then moves toward a rotary cutter that stamps out the biscuit fingers. Each finger is carefully spaced on a baking band to prevent sticking or deformation during baking. Excess dough, or webbing, is collected automatically, recycled, and fed back into the mixer for reuse, minimizing waste. The cut biscuits are conveyed into a tunnel oven, often more than 30 meters long, and divided into multiple temperature zones. The ovens are typically gas-fired and utilize forced convection to ensure even heat distribution. Baking profiles are carefully managed. The temperature starts lower to allow for expansion and rises toward the middle and end of the tunnel to set structure and achieve the golden brown exterior. The baking process typically lasts around 8 to 12 minutes. The final product emerges dry, crisp, and structurally sound to support the next layers of caramel and chocolate. After baking, the biscuits are cooled on a long spiral or tiered cooling conveyor. It is essential that they reach ambient temperature before caramel application, as residual heat could soften the caramel or cause bonding inconsistencies. Airflow systems within the cooling unit are calibrated to prevent moisture buildup, which could compromise the crispness of the biscuit layer. Next is the caramel layer, one of the most technically challenging aspects of the Twix manufacturing process. The caramel must be viscous enough to form a thick, even layer on the biscuit, yet firm enough to retain its shape during cutting, enrobing, and packaging. It must also stretch slightly when bitten into, without melting or breaking apart. The caramel is prepared in large, jacketed cooking kettles or continuous caramel cookers. The ingredients, glucose syrup, sugar, milk solids, fats, and sometimes salt and flavorings, are heated to a controlled temperature around 118 to 120 degrees Celsius. Cooking caramel to the correct temperature is critical. Any deviation can result in too hard or too runny caramel. The factory's automated control systems monitor brix levels, temperature curves, and viscosity in real time. Adjustments are made instantly if readings deviate from the set parameters. Once cooked, the caramel is pumped into a depositor system. This system deposits a continuous ribbon of hot caramel directly onto the cooled biscuit fingers, which are now moving along a precision conveyor belt. Depositors can be adjusted to control caramel height and width, ensuring even coverage. The The caramel must adhere firmly to the biscuit and cool rapidly to a semi-firm consistency to hold its shape through the subsequent chocolate enrobing process. The bars now enter a cooling tunnel for caramel setup. This tunnel is maintained at a lower ambient temperature and spans several meters to allow gradual cooling without thermal shock. As the caramel cools, it solidifies just enough to support chocolate coating without running or shifting. This balance is critical for appearance, structural integrity, and mouthfeel. Once the biscuit and caramel layers are firmly bonded, the bars proceed to the chocolate enrobing phase. This is where each Twix bar is fully coated in a layer of milk chocolate. The chocolate used is a proprietary blend formulated specifically for Mars, Inc. And it includes cocoa butter, milk powder, cocoa solids, sugar, and emulsifiers, such as soy lecithin, to ensure proper flow. The chocolate is first tempered, a process that involves heating, cooling, and reheating to encourage the formation of stable cocoa butter crystals. Proper tempering gives the final chocolate coating its shine, snap, and resistance to fat bloom. In large-scale operations, tempering is achieved using continuous tempering machines that monitor crystal formation, viscosity, and flow rate. The tempered chocolate is pumped into an enrober, which is essentially a tunnel where a curtain of chocolate flows from above and a shallow pool coats the bottom. The bars pass through this curtain and are submerged briefly in the bottom coating layer, ensuring all sides are covered. Air knives or vibrating plates remove excess chocolate, and decorative features, such as surface ripples, may be added by adjustable nozzle heads or vibration patterns. The chocolate-coated bars are immediately conveyed into another cooling tunnel, this one much longer and colder, designed to gradually bring the chocolate to a solid state without creating bloom or surface imperfections. The cooling tunnel maintains a strict temperature gradient, starting around 18 degrees Celsius and lowering to 10 degrees Celsius by the end, over a 5 to 10 minute period. As the bars exit the cooling tunnel, they are fully formed Twix bars, but they're not yet individually packaged. They move directly into the high-speed wrapping area. Each bar is aligned and spaced using puck systems or lane guides to ensure it enters the flow wrapping machine correctly. Here, rolls of branded film are fed into the wrapper, folded tightly around the bar, and sealed on all sides using heat and pressure. The film is pre-printed with logos, batch codes, nutritional data, and sometimes promotional graphics. Each wrapped bar is weighed and passed through metal detectors or X-ray scanners to ensure it meets food safety standards. Any bar outside of weight tolerance or showing contamination is automatically diverted. Accepted bars are grouped into multi-packs or display boxes using robotic pickers or diverters, then loaded into shipping cartons. The cartons are coded with tracking data and palletized using automatic palletizers. Each pallet is scanned into inventory and staged for shipping. Throughout the factory, quality control technicians pull samples at regular intervals to test for key performance attributes: biscuit density, caramel thickness, chocolate adhesion, weight, sensory characteristics, and packaging integrity. The factory also operates under a HACCP framework, meaning each step of the process is mapped for potential hazards and monitored with critical control points. Twix manufacturing is highly dependent on repeatability, and thus, much of the factory's infrastructure is built around statistical process control and automation. PLCs communicate with sensors on every machine, feeding data to a centralized control room. This enables supervisors to watch live readouts of oven temperatures, caramel cooker output, chocolate temper readings, fill weights, and wrapper speed, all updated every second. Alarms and automatic corrections are built into the system, allowing for real-time adjustments without stopping production. Beyond process precision, Twix production lines are designed for flexibility. Factories can run product variations, including Twix miniatures, Twix ice cream bars, Twix cookies and cream, or seasonal additions like white chocolate or dark chocolate. Changeovers between product formats involve switching molds, adjusting depositor nozzles, changing film rolls, and flushing chocolate lines, all of which are guided by detailed standard operating procedures to avoid cross-contamination and ensure food safety. Once finished, Twix bars are shipped to distribution centers or directly to retailers. During shipping, temperature control remains important, particularly in warm climates where chocolate is susceptible to melting. Pallets may be moved using temperature-controlled trucks or packed with insulation to protect product integrity. Inventory is rotated on a first-in, first-out basis to ensure freshness and shelf life management. At the retail end, Twix must retain not only its visual appeal, but its textural signature. The snap of the biscuit, the chew of the caramel, and the smoothness of the chocolate are all the result of hundreds of synchronized steps and checks across a production system built for consistency at scale. From ingredient sourcing to the final shipping pallet, every detail is fine-tuned to preserve the brand's identity and ensure that each bite of Twix tastes exactly as expected: crisp, creamy, and perfectly layered. The production of Starbucks products, particularly its packaged coffee offerings that end up in grocery stores, retail outlets, and international supply chains, begins long before a single bean is roasted. The entire process is built on one foundational element: green coffee sourcing. Starbucks, known for its commitment to quality and consistency, manages one of the most tightly controlled and globalized green coffee sourcing operations in the food and beverage industry. This first phase, the pre-roasting segment, is where the company sets the tone for every cup of coffee or bottled product it will eventually serve. And it's here we begin our highly detailed step-by-step journey. The green coffee sourcing process starts at origin, in the tropical coffee-growing regions that straddle the equator, primarily Latin America, East Africa, and Southeast Asia. Starbucks primarily uses Arabica beans due to their more nuanced flavor profiles compared to the hardier but less complex Robusta variety. Within the Arabica family, beans are selected based on elevation, soil composition, rainfall, and harvest timing. Starbucks maintains long-standing relationships with coffee growers, cooperatives, and export mills in countries like Colombia, Ethiopia, Guatemala, Indonesia, Brazil, and Rwanda. But it's not as simple as ordering beans in bulk and having them shipped. Starbucks uses a proprietary set of sourcing standards known as Coffee and Farmer Equity Practices. These standards are not only a requirement for suppliers to be eligible, but also a multi-layered auditing framework. CAFE practices address 4 critical areas: product quality, social responsibility, environmental leadership, and economic transparency. Every farm or co-op that sells beans to Starbucks must pass rigorous inspections in these categories, many of which are carried out by third-party auditors trained in agricultural and labor practices. Once a farm or producer is approved under CAFE practices, the beans are harvested, typically by hand. Hand picking ensures that only ripe coffee cherries are selected, an essential factor in achieving flavor consistency in the final roast. These cherries are then processed at or near the farm using either the washed method. The washed method involves removing the pulp and fermenting the beans to eliminate the mucilage before drying, producing a cleaner, brighter flavor. The natural method dries the entire cherry and imparts a fruitier, heavier profile. The method used depends on the country, the farmer's infrastructure, and the target flavor profile desired by Starbucks blending teams. Once processed, the green beans are dried to a specific moisture content, usually between 10% and 12%, and stored in parchment until they are ready for export. Before leaving the origin country, the beans undergo a final hulling process to remove the parchment layer. At this stage, Starbucks' quality assurance teams at origin perform multiple assessments. These include physical evaluations and cupping, an industry standard tasting method. Starbucks QA cuppers evaluate the green coffee on attributes like acidity, body, balance, sweetness, and aftertaste. Only those lots that meet Starbucks' sensory and structural requirements are approved for shipment. Approved beans are then packed into multi-layered jute bags with protective liners or into GrainPro plastic bags that guard against moisture and pests during transit. Each bag is tagged with a traceable barcode or lot number, which connects it to a digital database. This data includes not just the country and region of origin, but the exact farm or cooperative, harvest date, processing method, and quality score. This traceability is critical, not just for transparency and accountability, but also for quality replication year after year. Now begins the logistics phase. Starbucks contracts with specialized freight companies that understand the requirements of green coffee shipping. These beans are incredibly sensitive to temperature and humidity, even in raw form. A single exposure to high heat or excess moisture during transit can cause mold growth or flavor degradation. The beans are typically transported in temperature-stabilized shipping containers. If traveling by sea, the containers are outfitted with humidity control packs and dehumidifying systems. If air freight is used, the bags are carefully palletized, shrink-wrapped, and tagged with sensors that monitor environmental conditions throughout the journey. Upon arrival at one of Starbucks' roasting and manufacturing facilities, such as those located in York, Pennsylvania, Augusta, Georgia, Sandy Run, South Carolina, or Amsterdam, Netherlands, the green beans are unloaded, inspected, and entered into the factory's inventory management system. Before any production begins, each new shipment undergoes additional quality control. Samples from each bag or container are pulled and brought into the sensory lab. There, certified coffee graders perform cupping again, this time to ensure no quality loss occurred in transit. Moisture content, bean uniformity, and fragrance are retested. Beans that pass, these checks are tagged and routed to storage silos within the facility. These silos are food-grade, airtight steel vessels with internal climate regulation. Beans are stored based on variety, region, and intended blend. For example, Latin American beans destined for Starbucks blonde roast will be siloed separately from Ethiopian beans used in Starbucks Reserve offerings. Every silo is equipped with moisture sensors, thermometers, and pneumatic conveyor links, allowing operators to pull precise quantities for each roast batch according to master recipes. Before roasting can begin, beans are weighed into batches according to a specific ratio, depending on the blend being produced. Starbucks maintains an extensive library of proprietary blends, each with precise formulas. Some are single origin, where only one type of bean is used, while others, like Pike Place Roast or Espresso Roast, combine beans from multiple origins. Each blend is documented in the factory's recipe management software, which automatically calculates the needed amount of each component down to the gram and interfaces with weigh-scale systems to ensure accuracy. At this point, the beans are ready for roasting, but that process is highly intricate and deserves its own full analysis. Starbucks does not simply roast coffee by applying heat until the beans turn brown. The next step involves drum roasters, roast curves, heat profiling, airflow modulation, and real-time chemical transformation monitoring that will take the green coffee and convert it into the rich, aromatic, deeply flavored roasted beans that Starbucks is known for worldwide. With the green coffee beans now housed in precision-monitored silos and organized by blend formulation, the next phase of Starbucks' industrial production process transitions into what is often regarded as the heart of the entire operation: roasting. This stage is where the true transformation begins. The raw, pale green beans, earthy, grassy, and flavorless in their original state, are subjected to meticulously calibrated heat treatments that unlock their signature color, aroma, body, and complexity. Starbucks takes this phase extremely seriously, investing in proprietary roast profiles, customized equipment, and a multi-layered monitoring system to ensure that every batch matches the company's highly specific taste standards. The roasting process begins when a batch of green beans is called for from the storage silos. These silos are directly connected to the roasting equipment via stainless steel pneumatic transfer tubes. When an operator initiates a roast cycle, a preset quantity of beans, anywhere from 100 to 600 kilograms, depending on the size of the roaster, is discharged from the silo and transported through vacuum-sealed lines to the roaster's holding hopper. Here, the beans are pre-weighed on industrial platform scales connected to the plant's central production database, ensuring the exact quantity is delivered as dictated by the roast formula for that specific product, whether it's French roast, Pike Place, Sumatra, or espresso. Starbucks uses drum roasters for most of its large-scale production. These roasters consist of a rotating steel drum with an internal blade assembly that keeps the beans in constant motion. This ensures even exposure to heat as the drum is gradually raised to operating temperature, typically ranging between 190 degrees Celsius and 240 degrees Celsius, depending on the roast level. Lighter roasts, such as blonde roast, are roasted to lower final temperatures, while darker roasts, like French or Italian, require longer exposure and higher terminal heat. The roasting process follows a specific curve known as a roast profile. This is a data-driven graph that plots time against temperature, representing how heat is applied across the roast cycle. Starbucks profiles are proprietary and tightly controlled, with each product requiring a unique curve to deliver its intended flavor profile. These curves are not linear. They involve temperature ramps, plateaus, and even controlled dips. The initial drying phase lasts for several minutes, during which moisture is driven out of the bean. This is followed by the Maillard reaction phase, where sugars and amino acids begin to react, producing the rich brown coloration and the first wave of complex aromas. The most critical moment in roasting is known as first crack. This is when internal pressure in the bean causes it to physically crack open, producing an audible popping sound, much like popcorn. This marks a key transformation in bean chemistry. Starbucks roast operators listen for this moment, using audio sensors and thermal feedback to identify it precisely. Lighter roasts may be completed shortly after first crack, while medium and dark roasts continue through the development phase, where oils begin to emerge on the surface and flavor compounds deepen. Throughout this process, the roaster's control panel displays live data for bean temperature, exhaust temperature, airflow rate, and drum speed. The system is equipped with PID controllers and data logging software that feed into the factory's centralized SCADA system. Every roast is archived digitally, allowing Starbucks to recreate identical roast profiles across facilities on different continents, ensuring global consistency. Once the beans reach their designated roast level, they are immediately discharged from the drum into a cooling tray located below the roaster. This tray contains a rotating arm assembly that stirs the beans, while powerful fans blow ambient or chilled air upward from perforated grates below. Rapid cooling is essential to halt the roasting process and lock in the intended flavor and roast depth. If the beans are allowed to remain hot too long, they may bake, resulting in a flat, dull cup profile. The entire roasting to cooling process for a batch of coffee typically takes between 10 and 15 minutes, depending on the desired roast level and bean origin. Once cooled, the roasted beans are conveyed into degassing hoppers, stainless steel holding vessels, where the coffee rests for a short period, usually 12 to 24 hours. This rest period is necessary to allow CO2, a natural byproduct of roasting, to escape. If roasted beans are packaged too soon, the trapped gas can compromise packaging seals or even cause bags to inflate and rupture. However, some CO2 is desirable, especially for brewing freshness, so the timing of degassing must be carefully controlled. During this resting period, samples of each roast batch are collected and sent to the on-site sensory lab. Here, trained cupping teams evaluate the beans using controlled brewing and tasting protocols. They assess key attributes like aroma, acidity, balance, mouthfeel, finish, and overall quality compared to Starbucks' master profile for that roast. Cupping is performed blind and in duplicate to eliminate bias and ensure accuracy. If a batch falls outside of the acceptable range, it may be blended with other batches to correct the profile, used for internal consumption, or in rare cases, discarded. Once a roast batch passes quality inspection, it is routed towards the grinding and packaging area. Some products, like whole bean offerings, will skip the grinding stage entirely, while others destined for ground coffee bags or capsules will be milled using precision grinders. These machines are fitted with hardened steel burrs or rollers that crush the beans to an exact particle size distribution. Starbucks defines specific grind profiles depending on brewing method. For example, drip coffee grind is coarser than espresso grind, and French press is coarser still. Grinding is a highly sensitive operation. During the process, friction from the burrs generates heat, which can degrade volatile aromatics if not carefully controlled. To counter this, industrial grinders are equipped with chilled air systems and thermocouple sensors that regulate burr temperature and prevent overheating. In many facilities, grinding is conducted in a temperature-controlled room or during cooler hours of the day to preserve freshness. As soon as the coffee is ground, it moves to packaging, often through vacuum-sealed transfer tubes that prevent oxidation. The packaging stage is designed to preserve flavor and aroma while ensuring shelf stability. Starbucks uses multi-layer barrier films for its ground coffee products. These films include aluminum or metallized polyester layers that block oxygen and moisture. Many packages are fitted with one-way degassing valves that allow CO2 to escape without letting oxygen in, protecting the coffee's integrity while preventing package ballooning. Packaging machinery includes vertical form fill seal systems for smaller bags and horizontal form fill seal machines for pillow packs or multi-packs. Each package is filled to a specific weight, sealed, and coded with production data, including roast date, location, shift, and lot number. High-speed check weighers and vision systems verify fill accuracy, seal integrity, and barcode clarity. Any package that fails inspection is automatically diverted off the line for rework. After packaging, the coffee products are grouped into cases and transferred to automated case packers and palletizers. Pallets are wrapped and labeled, then stored in temperature-controlled warehouses before shipping. These final steps, inventory control, cold chain monitoring, and outbound logistics, are critical to ensure the roasted Starbucks product reaches distribution centers and retail shelves around the world in optimal condition. With the coffee beans now expertly roasted, cooled, rested, and either packaged whole or ground and sealed, Starbucks' industrial production extends into another critical manufacturing domain, the preparation of its ready-to-drink beverages. These include bottled frappuccinos, chilled espresso drinks, cold brews, and dairy-based coffee blends. These products are not created in the same facilities that handle roasting and bagging. Instead, Starbucks partners with specialized beverage manufacturing facilities. Many cooperated with industry leaders like PepsiCo through the North American Coffee Partnership to manage this high-volume cold fill production. This stage involves liquid formulation, blending, thermal processing, homogenization, and sterile packaging under rigid food safety standards. The process begins with the formulation of the beverage base. For a bottled frappuccino, for example, this includes several core ingredients: brewed coffee extract, filtered water, sugar or corn syrup, dairy or dairy alternatives, stabilizers, and natural or artificial flavorings like vanilla, caramel, or mocha. Each component must be handled separately with precision before it's brought into the blending system. Coffee extract is typically delivered in concentrated form, produced by either brewing Starbucks beans at scale or using advanced extraction methods like cold concentrate percolation or high-pressure brewing. This extract arrives in refrigerated, food-grade totes or tanker trucks, depending on batch size. Upon arrival, it is sampled, analyzed for strength, and approved by the on-site quality control team before entering the liquid ingredient holding tanks. Simultaneously, dairy components such as milk and cream are received through chilled pipelines or aseptic bag-in-box systems. Dairy intake systems in Starbucks RTD plants are equipped with plate heat exchangers to quickly chill and store milk at temperatures below 4 degrees Celsius to maintain freshness and prevent bacterial growth. If using shelf-stable milk or UHT-treated dairy, the plant will still hold the product under cold storage until use. For plant-based SKUs, oat milk, almond milk, or soy milk are stored and handled in similar systems, albeit through dedicated lines to avoid allergen cross-contamination. Sweeteners and stabilizers such as sugar, corn syrup solids, carrageenan, cellulose gum, and pectin are weighed and pre-mixed in separate tanks. Starbucks beverages are engineered not just for taste, but for texture, mouthfeel, and visual consistency, especially in cream-based products like bottled mochas and vanilla frappuccinos. The stabilizers help suspend coffee solids, prevent dairy separation, and ensure the beverage maintains a smooth, homogeneous appearance on shelf, even after weeks or months in cold chain storage. All of these components, coffee extract, dairy or alternative milk, sweeteners, water, and flavor compounds, are brought together in the blending system. This usually consists of large stainless steel jacketed mixing tanks ranging from 1,000 to 5,000 liters. Each tank is equipped with an internal agitator, a bottom-mounted high-shear mixer, and in some cases, inline emulsifiers or homogenizers to ensure all elements are fully integrated. Tanks are fitted with load cells and flow meters, enabling automated dosing of each ingredient according to pre-programmed batch recipes. The blending system is monitored via a central control unit, typically a PLC-connected touchscreen interface that displays real-time values for temperature, mixing speed, pH, and ingredient flow. Operators can monitor the tank's temperature curve, the shear level during mixing, and the dwell time of each phase. In a typical Starbucks RTD batch, the blending cycle lasts between 30 and 60 minutes. During this time, inline sensors monitor turbidity, Brix, and viscosity. Samples are taken periodically to verify pH, flavor intensity, and microbial load before the batch is cleared for downstream processing. Once the beverage blend is complete and validated, the next stage is thermal processing. Most Starbucks RTD beverages are pasteurized using high-temperature, short-time systems, which allow for rapid heat treatment without compromising taste or texture. In HTST, the product is pumped through a heat exchanger that raises the liquid temperature to 85 degrees Celsius to 95 degrees Celsius for 15 to 30 seconds, then rapidly cools it to filling temperature, usually between 4 degrees Celsius and 10 degrees Celsius for cold fill lines, or slightly higher for hot fill bottles. This process effectively destroys any pathogenic microbes while preserving the coffee's aroma and flavor. Some facilities use ultra-high temperature processing for shelf-stable lines, allowing the product to remain unrefrigerated until opened. In UHT, the beverage is flash heated to temperatures up to 140 degrees Celsius for just a few seconds, then cooled quickly before packaging. The decision between HTST and UHT depends on the specific product's shelf life goals, packaging type, and distribution model. Immediately following thermal processing, the beverage passes through an inline homogenizer. This device applies intense pressure, often in excess of 2000 psi, to the liquid through a narrow valve, breaking down fat globules and suspended solids into microparticles. This step is critical for emulsion stability, preventing the cream from separating from the coffee or the flavor oils from rising to the surface. Homogenization also improves mouthfeel, making the beverage taste creamier and smoother. From here, the liquid is conveyed to the filling system. Starbucks RTD products are filled into a variety of package types: PET bottles, glass bottles, aluminum cans, and aseptic cartons. Each format requires its own dedicated filling and sealing system. For bottled frappuccinos, a cold fill rotary filler is typically used. This high-speed machine feeds sterilized bottles onto a rotating platform, where they are filled by gravity or volumetric fillers to exact fill levels. Immediately afterward, caps are applied, using steam-assisted capping heads to ensure a vacuum-tight seal and tamper resistance. Cans and cartons are filled on their respective lines, cartons often using form-fill-seal machines that shape the container, fill it, and seal the top in one continuous motion. All packages pass through automated detection systems that verify fill levels using weight sensors, check cap placement with vision systems, and scan barcodes to confirm packaging accuracy. Reject mechanisms immediately remove any container that fails these criteria. The filled beverages are then passed through a secondary cooling tunnel or refrigerated spiral conveyor that ensures they reach their final holding temperature before entering the packaging area. Depending on the product, this may be as low as 2 degrees Celsius, especially for refrigerated drinks destined for grocery and convenience store cold vaults. Once cooled, the individual containers are collected into multi-packs, shrink-wrapped, and placed into branded cartons. These cartons are then palletized by robotic arms and wrapped with plastic film. Each pallet is labeled with a unique identifier, linking it to the specific batch number, production date, filler line, and formulation ID. All of this information is uploaded into the factory's ERP system, providing full traceability from bean to bottle. Before any shipment is cleared, final product samples are pulled from each pallet for comprehensive testing. These include microbial testing, shelf stability stress tests, and sensory evaluations by trained panels. Only after all tests are passed are pallets released into refrigerated distribution channels for delivery to retail partners, Starbucks cafes, or direct-to-consumer platforms. From formulation and blending to pasteurization, homogenization, and ultra-clean packaging, this RTD production phase represents one of the most technologically advanced parts of Starbucks' global supply chain. It's where liquid meets logistics, combining industrial food science with tight controls over quality, taste, and branding. Every chilled bottle or can represents thousands of interconnected variables managed with absolute precision to deliver a consistent, enjoyable Starbucks experience anywhere in the world. With Starbucks ready-to-drink beverages now filled, sealed, chilled, and palletized, the focus shifts to the final, but no less complex, elements of factory operations. Sustainability integration, byproduct management, batch auditing, and outbound logistics. While the product may appear finished at this stage, the systems behind its release are still active, ensuring every bottle or can shipped reflects the brand's uncompromising quality, environmental responsibility, and traceability. One major component of this final phase is waste stream management. Every Starbucks beverage production facility is designed to minimize waste and make use of byproducts wherever possible. Coffee grounds remaining from extract production are collected and either sent to composting facilities, transformed into animal feed, or, in more advanced plants, used as biomass fuel to generate energy. Spent dairy materials or cleaning water are filtered and treated through on-site wastewater management systems, often returning grey water to municipal treatment plants within strict pH and chemical parameters. Packaging waste, including edge trims from shrink wrap film, carton misprints, and PET bottle scrap, is separated and sent to in-factory compactors and balers. These bales are transported to certified recyclers for reprocessing. Starbucks has implemented programs at several manufacturing locations that convert unrecyclable soft plastics into composite shipping pallets or building materials, helping close the loop on production materials. In parallel with waste management, quality auditing continues even after packaging. Randomly selected finished products are pulled from every batch and routed to a dedicated quality assurance lab within the facility. There, they undergo another round of microbiological testing, sensory analysis, packaging integrity checks, and accelerated aging simulations. These simulations might involve storing the product at elevated temperatures for several days or weeks to mimic what could happen during prolonged distribution delays. Any deviation in flavor, appearance, or microbial safety can trigger a hold on the entire batch while root causes are investigated. All data generated, from roast date to filler head temperature, from pallet wrap tension to microbial test results, is logged in the facility's centralized manufacturing execution system. This digital record ensures that any shipment can be traced back through every step of the factory process. If a product recall is ever initiated, these logs allow immediate identification of affected units by date, location, and even by hour of production. When cleared, the finished pallets are scheduled for outbound logistics. Route planning software, inventory analytics, and order data from Starbucks' retail and grocery distribution teams are combined to determine where each batch will go. Products destined for grocery stores enter the cold chain system, transported in refrigerated trucks with temperature logs monitored in real time. Others, such as shelf-stable offerings, are routed to ambient storage hubs or export terminals for international shipping. The production of Domino's pizza begins not in the store kitchens, but in massive regional supply chain centers, where the ingredients, particularly the dough, are produced in industrial quantities with an emphasis on consistency, quality, and efficiency. Before any pizza reaches the oven in a Domino's franchise, it starts its journey in these highly controlled factory environments, where each element is formulated to exact specifications. The first and most critical component is the dough, which is made fresh daily in these centers and delivered under cold storage conditions to every Domino's outlet. The dough making process begins with the arrival of bulk ingredients, including high-protein wheat flour, water, vegetable oil, yeast, sugar, and salt. These ingredients are stored in separate storage systems based on their physical state and volume requirements. Flour is kept in massive silos connected to the production floor through pneumatic tubing systems. These tubes transfer flour directly into the industrial-scale mixers with precise weight measurements, controlled by automated batching systems. Water, which must be maintained at a specific temperature range to activate the yeast properly, is stored in stainless steel tanks connected to digital flow meters. This ensures the exact volume is dispensed into each batch, typically to within 1/10 of a liter. Vegetable oil, sugar, salt, and yeast are also dispensed through closed-loop systems that prevent contamination while ensuring high-speed delivery and accuracy. The industrial mixers used at this stage are horizontal high-capacity spiral mixers or fork mixers, depending on the location and the specific equipment model in use. Each mixer is designed to handle hundreds of pounds of dough per batch, usually around 400 to 600 pounds. The process begins with dry ingredients being added first, followed by a controlled stream of water and oil. Once the mixture reaches the desired hydration point, the mixer operates at different programmed speeds to knead the dough until it reaches the correct elasticity and gluten development. This usually takes around 8 to 10 minutes, with temperature sensors embedded in the bowl to prevent overheating from friction, which can damage the yeast. As the dough mixes, Factory floor operators monitor each batch's time, temperature, and consistency through a computerized interface. Every mixer is part of a larger manufacturing execution system that records batch data, ingredient lots, timestamps, and operator IDs. This traceability system ensures that if a problem ever arises, such as inconsistent rise or poor texture in a batch, managers can track it back to the specific flour lot or mixing time and make necessary adjustments for future runs. Once the dough reaches optimal consistency, it is automatically discharged from the mixer into a dough trough, which is essentially a wheeled stainless steel container that holds the dough until it's moved to the dividing station. The dough is then transferred into a hopper above a hydraulic or rotary dough divider. This machine uses either vacuum-assisted suction or mechanical cutting blades to portion the dough into uniformly weighted balls, typically ranging from 6 to 20 ounces, depending on the final pizza size. Each portion is measured by load cells, digital weighing systems that maintain accuracy within a few grams. These dough balls then proceed to the rounding machine, which takes each divided piece and rolls it into a tight, smooth sphere. This is crucial for creating the internal tension needed for a uniform rise during fermentation. The rounding machine uses rotating plates or belts that apply gentle pressure and a circular motion to the dough. After rounding, the dough balls are dusted lightly with food-grade flour or semolina to prevent sticking, and then placed into oiled dough trays. These trays are stacked and covered with plastic lids or wraps to maintain humidity and prevent surface drying. They're labeled with a printed barcode that includes the production date, time, dough type, and batch number. At this point, the dough enters the proofing phase, which is critical to developing both the structure and flavor of the final pizza base. Proofing occurs in temperature and humidity-controlled rooms, where racks of dough trays are stored for several hours. The ideal proofing conditions are generally around 80 degrees Fahrenheit with 75% relative humidity, although this can vary slightly based on factory location and yeast activity. The yeast begins to consume the sugars in the dough, producing carbon dioxide and ethanol as byproducts. This gas becomes trapped within the dough's gluten network, causing it to expand and develop the characteristic airy, chewy structure. Simultaneously, organic acids and alcohols created during fermentation start to build complex flavor notes in the dough. During the proofing period, plant operators conduct regular checks to monitor dough expansion, surface tension, and even internal temperature using infrared thermometers and visual inspection. Some factories use automated camera systems that scan the trays and calculate proofing progress by measuring the dough's rise and dome shape. Any deviations from the standard profile are flagged for intervention, whether that means extending the proofing time or moving certain trays to a different section of the proofing room. Once the dough reaches the desired level of fermentation, it is moved to the cold storage phase. In this stage, the dough trays are rolled into large walk-in refrigeration rooms, where the temperature is maintained at approximately 2 to 4 degrees Celsius. This halts the yeast's activity and locks in the developed flavor while also preventing overproofing. The chilled dough can now be stored for up to several days, depending on demand at the destination stores. During this time, the trays are rotated to maintain even cooling and are occasionally inspected for signs of over-fermentation or drying. While the dough is being prepared, Domino's is also handling the sauce production in parallel. Tomato sauce is made in separate processing areas, using high-volume stainless steel kettles equipped with agitators and heating jackets. The base of the sauce is tomato paste, which is diluted with water to reach a specific consistency. To this, measured quantities of salt, sugar, oregano, garlic, basil, black pepper, and other proprietary spices are added. Some locations use pre-mixed spice sachets that are batch-coded for accuracy, while others blend the seasoning on site. The sauce mixture is heated to temperatures between 80 and 90 degrees Celsius to sterilize it and meld the flavors. Once the heating process is complete, it is rapidly cooled using a plate heat exchanger to bring it down to refrigerated storage temperature, usually 30 degrees Celsius, around 4 degrees Celsius. The cooled sauce is then transferred into food-safe storage containers, often in 10-liter or 20-liter units, and sealed with tamper-evident caps. Each container is labeled with a batch code and production date before being staged for shipment alongside the dough. In addition to sauce, the factory prepares other key ingredients, including shredded cheese and select toppings. The cheese used in Domino's pizzas is typically a low-moisture mozzarella, known for its excellent melting properties and stretch. Some supply centers receive the cheese in bulk blocks and shred it in-house using high-speed rotary shredders that slice the blocks into uniform strands. The shredding process includes a light coating of anti-caking agents like potato starch or cellulose to prevent clumping during storage. The shredded cheese is packed into portioned bags, vacuum sealed, and stored under refrigeration. Once all ingredients, dough, sauce, cheese, and prepped toppings are ready, they are organized and loaded into refrigerated delivery trucks. These trucks operate under a tight logistics schedule, making daily or multi-day trips depending on the volume needs of each Domino's franchise store. The internal temperature of each truck is continuously monitored using GPS-integrated data loggers, and real-time data is fed back to the supply center's central operations system. This ensures that if any deviation in temperature or route timing occurs, corrective action can be taken immediately. By the time the products arrive at the store, they are fully prepared and only require assembly and baking. The franchise stores then execute the final steps of pizza preparation, which involves pressing out the dough, saucing, topping, baking, and packaging. However, the factory's role is absolutely central to ensuring that every ingredient arrives at the exact same standard, no matter where the pizza is being made or consumed. Through this centralized and automated model, Domino's achieves consistency at a global scale, while minimizing waste and human error in the earliest and most foundational stages of production. Once the refrigerated trucks deliver the dough, sauce, cheese, and toppings to each Domino's franchise, the handling of those ingredients transitions from centralized factory production to carefully structured in-store processes that continue to follow standardized protocols. However, the factory's influence is far from over at this point. The store-level procedures are engineered to mirror the consistency, precision, and speed found in the supply chain centers, effectively extending the factory environment into each retail location. Inside the store, the first critical action is the proper storage of the dough. As the dough trays arrive straight from cold storage, they are transferred into the store's walk-in refrigerator, where they are kept at a consistent temperature of 2 to 4 degrees Celsius. Each dough tray remains sealed with its identifying barcode, which includes the production batch, date, and shelf life. This code is scanned upon arrival, logged into the store's inventory system, and linked to the store's daily forecast so the staff can prioritize older dough for earlier use, following a strict first in, first out system to ensure freshness and prevent waste. Before the dough can be used for making pizzas, it needs to temper. Cold dough straight from refrigeration is too stiff and contracted to stretch evenly or bake correctly. Therefore, several trays are pulled from the cooler in staggered intervals and placed in a proofing area within the store, typically kept at room temperature for 30 to 60 minutes. During this period, the dough relaxes, allowing the gluten to become more extensible and the yeast to reawaken slightly, which enhances browning and flavor development in the oven. This step also restores some of the softness and elasticity necessary for the dough to perform consistently on the preparation line. The next key phase in the process is dough pressing or hand stretching, which transforms the proofed dough ball into a pizza base. Depending on the store's equipment and regional preferences, Domino's uses one of several standard methods for this. In many high-volume locations, a mechanical dough press is employed. This press is a heated platen system where a single dough ball is centered between two metal plates. With controlled pressure and temperature, the plates compress the dough to the specified diameter and thickness. The brief heat exposure also helps to set the edge of the crust slightly, which prevents overexpansion during baking. Other stores use hand stretching techniques, which involve manually flattening the dough using the palms and fingertips to create an even disc, often followed by a gentle spinning motion to widen it to the correct diameter. Employees are trained to feel for even dough resistance, check the uniformity of thickness, and ensure the edges are slightly thicker to create the signature Domino's crust ring. Some locations employ a dough sheeter, a machine that flattens dough between two adjustable rollers, which is commonly used for medium thickness crusts or thin crust options. Once the dough is properly shaped and placed on a pizza screen or baking tray, it is ready to be sauced. The sauce comes in pre-measured containers or large bag-in-box systems with pump dispensers, depending on the store's volume. A standardized rotary sauce ladle or domed saucer is used to apply a precise amount of sauce, usually between 90 and 120 grams for a medium pizza. The sauce is spread using a circular motion that stops approximately 1 inch from the crust edge to allow for natural bubbling and rim development during baking. With the base sauced, the next step is the cheese application. Domino's cheese is a proprietary, low-moisture mozzarella blend, optimized for melt, stretch, and browning. The cheese arrives shredded in sealed, chilled bags and is stored in under-counter refrigeration near the prep stations for quick access. Employees use color-coded scoops to portion out exact grams of cheese per pizza size: small, medium, large, or extra large. This consistency ensures that the cheese melts evenly and that the nutritional and caloric values remain standardized. In high-throughput stores, preloaded portion dispensers or weigh scales may also be integrated into the cheese station to reduce time and improve accuracy. Next, the pizza moves to the topping stage. Domino's toppings, such as pepperoni, Italian sausage, mushrooms, green peppers, onions, olives, jalapenos, grilled chicken, and bacon, are kept in ingredient rails with stainless steel pans, maintained at safe refrigeration temperatures using undermounted chillers. Each topping has a designated scoop or set of tongs, and employees are trained to apply the correct amount and distribution per pizza size and recipe. Toppings are applied in a set sequence to ensure even cooking and consistent flavor layering. For example, pepperoni slices are laid edge to edge to cover the surface in a signature circular pattern, while sausage crumbles are more scattered to allow airflow between pieces. Vegetables are typically added last, as their moisture content can impact the crispness of the crust if layered too deeply. Domino's uses laminated guides and portion charts to ensure that every pizza, regardless of who's preparing it, looks, weighs, and tastes the same. With the pizza fully assembled, it is placed onto a conveyor belt oven, also known as an impingement oven. This oven style uses jets of superheated air blasted from top and bottom to ensure even baking. The oven belt is set to a precise speed, generally resulting in a 5.5 to 7 minute bake time, depending on the pizza size and topping density. The oven's digital interface allows staff to select different profiles for thin crust, hand-tossed, deep dish, or extra cheese options. Each profile adjusts air velocity, top and bottom heat ratio, and belt speed to produce the ideal bake for that style of pizza. During baking, several chemical and physical transformations take place. The crust expands slightly. From the final stage of yeast fermentation, steam is released from the sauce and toppings, and the cheese melts and begins to brown through the Maillard reaction. Excess moisture from vegetables is evaporated by the oven's airflow, ensuring the crust remains crisp and doesn't sag. The pizza emerges from the other side of the oven, fully baked and ready for slicing. At the end of the conveyor, pizzas are transferred to a staging counter, where they rest for 20 to 30 seconds to allow the cheese to set slightly. Then, using a rocker blade or circular pizza cutter, employees cut the pizza into standard portions, usually 8 slices for a large pizza, based on Domino's cutting guides. Each pizza is then slid into a branded corrugated cardboard box, which is specially designed with vent holes and moisture-absorbing liners to preserve crispness during delivery. Every box is sealed and receives a printed label generated by the store's order management system. This label includes the customer's name, order number, timestamp, and pizza specifications. For orders placed online or through the app, this also triggers an update on Domino's proprietary pizza tracker, which uses real-time data from kitchen sensors to notify customers of each stage, from dough prep to oven entry, baking, boxing, and out for delivery status. Throughout the day, all these processes are monitored for compliance with Domino's global standards. District managers conduct regular audits using detailed checklists covering dough handling, oven cleanliness, bake quality, topping accuracy, and safety procedures. Additionally, Domino's has built-in kitchen timers and alert systems that ensure no dough is held at room temperature too long, no pizzas sit unboxed beyond the quality threshold, and no ingredients are used past their hold times. Each store's operations are built to match the precision and consistency of the supply chain factories. In fact, many stores undergo periodic retraining sessions to realign their practices with the upstream factory procedures. This ensures that no matter how far the finished product is from the centralized dough production, the final experience to the consumer remains nearly indistinguishable between one location and the next. As soon as a Domino's pizza is sliced and boxed, the journey continues into a carefully engineered phase focused on preserving product quality and maximizing delivery efficiency. At this point, what might appear to the customer as the simple act of putting a pizza in a box and sending it out the door is, in reality, a continuation of Domino's factory-grade systems, refined, tracked, and executed with industrial precision. Each Domino's box is made of specially designed corrugated cardboard, engineered not only to be structurally strong enough for stacking and transportation, but also to allow moisture control and thermal retention. Small vent holes are strategically placed around the box edges to allow steam to escape without sacrificing internal heat. This is critical to maintaining a crisp bottom crust while keeping the cheese and toppings hot and intact during transit. The liners inside some specialty pizza boxes also use grease-resistant coating and moisture-wicking micro layers that reduce sogginess, especially in pizzas with heavier vegetable or meat toppings. Once the pizza is placed in its box, a label is immediately printed and applied. This label contains all relevant details: the order number, pizza type, time of bake, the customer's name and address, and specific cooking instructions if applicable, like extra crispy crust, light sauce, or no cheese. More importantly, the label also includes digital timestamps and batch codes that tie the finished product directly back to every earlier phase of production. These codes link the order to its dough batch, sauce mix, cheese lot, and even the name of the employee who boxed it. This allows full traceability, and in the event of a customer complaint or quality issue, managers can pull up detailed records to investigate and resolve the problem efficiently. The next link in the process is the delivery system, which Domino's has industrialized to a level similar to its supply chain and production operations. Every Domino's location uses a centralized digital system to optimize delivery routes, monitor driver location, and track pizza temperature using estimated time-to-door algorithms. In some urban areas or flagship locations, Domino's even uses thermal sensors and GPS modules in the delivery bags themselves. These sensors ensure that the pizza never drops below the acceptable temperature threshold, typically around 140 degrees Fahrenheit or 60 degrees Celsius, which maintains cheese integrity and topping stability. The delivery bags used are not basic insulated containers. They are purpose-built thermal sleeves with advanced insulation material, sometimes incorporating phase change materials that hold heat without overheating the product. These bags are lined with aluminum and closed with Velcro or zippers to ensure no heat escape. In some pilot programs, Domino's has experimented with electrically heated delivery pouches that plug into the vehicle's charging outlet, maintaining a regulated temperature across the entire delivery window, especially in colder climates. While the pizza is en route, Domino's proprietary pizza tracker remains active. This cloud-based interface receives inputs from multiple sources: the POS system, kitchen sensors, label printer, and delivery dispatch terminal, and creates real-time updates for the customer. As soon as the order is marked out for delivery, a countdown begins based on predictive delivery timing, factoring in distance, time of day, historical traffic data, and driver availability. This transparency not only improves customer satisfaction, but also provides performance data for internal use. Behind the scenes, Domino's aggregates all this operational data into their enterprise-wide performance dashboards. Each store's key performance indicators, such as order accuracy, delivery time, baking efficiency, and customer satisfaction scores, are updated daily. Store managers and regional supervisors review these metrics in regular meetings, identifying trends, deviations, and opportunities for improvement. If a certain franchise location consistently shows slower bake times or increased complaints about cold pizza, it may trigger a maintenance review of the oven system or retraining of kitchen staff. Meanwhile, at the supply chain level, Domino's uses reverse logistics to complete the factory-style loop. Once a delivery is completed, used ingredient bins, dough trays, and empty sauce containers are returned to the regional supply centers on the next inbound truck trip. These items are cleaned, sanitized, and reused according to food safety protocols. Reusable dough trays, for example, go through automated washing systems that use high-pressure jets, detergent, and thermal sanitation to prepare them for the next production cycle. By managing both outgoing and incoming flows efficiently, Domino's minimizes waste and maximizes logistical efficiency, keeping the system sustainable and cost-effective. Beyond the visible kitchen and delivery operations, there is also a sophisticated forecasting and inventory management system that relies heavily on factory data. Using AI and machine learning, Domino's forecasts demand for dough, sauce, cheese, and toppings at each store based on variables like local events, weather, historical order volumes, and even social media trends. This information is transmitted back to the supply chain centers, which adjust dough production and ingredient packaging accordingly. For example, if a city is expecting a snowstorm, the system may predict a spike in delivery orders and increase dough production by 10% for the affected stores. This tight integration between forecasting and factory production minimizes spoilage and overproduction, ensuring that only as much dough and sauce is produced as will be used within a defined freshness window. The same logic applies to toppings and cheese. Ingredients that are nearing the end of their shelf life can be flagged automatically, prompting store managers to run promotional offers or bundle deals to encourage faster turnover. By linking the retail environment back to the factory floor, Domino's achieves a level of responsiveness and precision rarely seen in traditional food service operations. Domino's also incorporates periodic updates and R&D feedback into its manufacturing systems. When a new product is launched, such as a specialty crust or a new line of toppings, the manufacturing centers adapt their formulations and packaging processes to accommodate the change. For instance, a new crust option may require a dough with a different hydration level or proofing profile. In that case, dough mixers are recalibrated, proofing room settings adjusted, and additional QA steps introduced. The product launch timeline includes upstream changes that affect every supply chain center, down to the labeling system and transport logistics. To maintain global brand consistency, Domino's has standardized its production protocols across all countries, yet also incorporates regional customization. For instance, the dough produced in India may include slight formulation changes to better suit local humidity levels or flour types. In Japan, where crust styles vary, dough mixing and resting procedures may be adapted for fluffier or rice-infused bases. However, the core manufacturing principles, precise batching, automated mixing, cold chain delivery, and digital inventory tracking, remain consistent regardless of geography. Domino's also performs routine auditing and calibration of their supply chain centers to ensure continued alignment with performance standards. Factory equipment such as mixers, dividers, and temperature control units are subjected to preventive maintenance and calibration checks at regular intervals. Technicians verify dough density, elasticity, and yeast activity using physical measurements and digital readouts. Similar checks are done for sauce viscosity, cheese fat content, and topping moisture levels. These numbers are logged and analyzed to identify any drift from target specifications, allowing corrective measures to be implemented before product quality is affected. Even packaging materials go through quality control. Corrugated boxes are tested for burst strength, fold endurance, and thermal retention properties. Adhesives used for box sealing are food safe and resistant to temperature extremes. The printing quality on labels is monitored to ensure clarity and durability, as these labels serve both customer-facing and internal traceability functions. Everything down to the ink used on packaging is selected for durability under heat and moisture, a testament to the factory-level thinking that permeates the entire Domino's ecosystem. Historically, gum base was made from natural tree resins like chicle, a latex-like substance harvested from the sapodilla tree, which grows in Central America. However, nearly all modern bubblegum factories now rely on synthetic gum bases. These are specially formulated blends of food-grade elastomers, resins, waxes, plasticizers, and softening agents. The use of synthetics provides far greater control over consistency, shelf life, and bubble blowing capability, which is critical for mass production and distribution. The raw materials used in synthetic gum base are delivered to the factory in large sacks or drums, and each ingredient is sampled and tested before entering the production line. Elastomers such as polyisobutylene and polyvinyl acetate provide the stretchy, elastic properties needed for bubble blowing. Resins act as binders that hold the gum together. Waxes like paraffin and microcrystalline waxes are added to soften the mixture and give the gum its pliable, non-brittle chew. Plasticizers such as glycerol, esters improve texture, while fillers like calcium carbonate or talc give the gum body and density. Each of these materials must be prepared for mixing. Solid components are broken down using industrial grinders and micronizers to achieve a uniform particle size, which ensures even distribution throughout the base. Waxes and resins are often pre-melted in jacketed stainless steel tanks equipped with indirect heating systems to prevent scorching. The raw elastomers are delivered in dense, rubbery blocks that are cut down using industrial dicing equipment before being added to the mix. Accuracy in measuring each component is vital. The slightest deviation in the amount of resin or wax can drastically alter the final chewiness and bubble-forming capability of the gum. Now it's time for the blending of the gum base, which happens in large Sigma blade mixers, named for their two interlocking Z-shaped blades that rotate in opposite directions to fold and knead heavy materials. These mixers are specifically designed to handle high viscosity compounds like gum base. The various pre-measured ingredients are added to the mixer in a specific sequence. First, the elastomers are introduced and given time to soften and break down under shear force. As they begin to form a uniform mass, resins are added to bind the structure. Waxes and plasticizers follow, blending smoothly into the mixture to help reduce internal friction and improve processability. This mixing process is not quick. Depending on the size of the batch and the recipe, the blending cycle can last anywhere from 45 minutes to several hours. The mixer itself is equipped with internal thermocouples to continuously monitor the temperature of the mass, which is maintained between 60 degrees Celsius and 90 degrees Celsius. Too low and the materials won't melt and blend. Too high and thermal degradation could occur, affecting the safety and performance of the gum. Operators observe the process through viewing ports and rely on torque readings and viscosity data from the mixer's internal sensors to determine the exact moment the gum base is fully homogenized. Once the gum base has reached the correct consistency, it is discharged from the mixer. This is a challenging step because the base at this point is extremely thick, sticky, and hot. To facilitate removal, the bottom of the mixer opens hydraulically and the heavy base is dropped onto a large stainless steel cooling table or fed directly into a sheeting system. The cooling table is actively temperature controlled using circulating chilled water to begin lowering the temperature of the gum base as quickly and evenly as possible. Large Teflon-coated rollers may be used to flatten the mass slightly, increasing surface area and speeding up the cooling process. The goal at this point is not to bring the base down to room temperature entirely, but to reduce its temperature to a workable range, usually between 40 degrees Celsius and 50 degrees Celsius, so it can move to the next stage without sticking to equipment or losing its plasticity. The partially cooled gum base is then cut into manageable blocks using high lubricity heated cutting blades. These blocks are weighed, labeled with batch numbers, and either sent directly to the next phase of production or stored in temperature-controlled holding rooms for later use. Even in this early stage of production, quality control is already an active part of the process. Samples of gum base are collected from each batch and taken to the plant's in-house laboratory, where technicians test them for elasticity, tensile strength, softness, and melt behavior. Specialized equipment such as rheometers, durometers, and texture analyzers are used to measure mechanical properties under simulated chewing conditions. This ensures that the gum base will respond correctly when blended with sweeteners, flavors, and colors in the next stages of processing. It's also worth noting that not all gum base formulations are the same. For bubblegum specifically, the formulation includes higher levels of elastomers and plasticizers than in chewing gum intended for long-lasting flavor or dental benefits. Bubblegum is designed to be more pliable and capable of trapping air, so it can form large bubbles without breaking too easily. This performance requirement influences everything from ingredient selection to mixer settings and even downstream cooling methods. Therefore, each variation of gum base may require its own unique process settings and equipment parameters. In the next stage, the base will be transferred into another high-capacity mixer, this time designed to handle not only dense material, but also sensitive flavor components and volatile sweeteners. The balance of heat, pressure, timing, and sequencing here is critical. Too much heat can break down sugar molecules and destroy flavor integrity. Too little, and the gum won't mix properly. The entire system must operate like a symphony of mechanical precision and food engineering science to ensure that every piece of bubblegum delivers the iconic chew and flavor burst that consumers expect. With the gum base now fully prepared, cooled, and tested, it's time for one of the most critical stages in bubblegum manufacturing: the integration of sweeteners, softeners, and flavorings. This is where the bland, rubbery core transforms into something enjoyable and familiar. The sweet, fruity, chewy product capable of inflating into perfect pink bubbles. At this point, the gum base is still a nondescript mass, pliable, tacky, but utterly flavorless and unappealing. The magic is about to happen in an industrial mixing process that must blend these next components evenly while preserving the precise texture and chew required for successful bubblegum performance. Before anything is added to the gum base, it must be brought back to a specific working temperature. Though the blocks were cooled after being discharged from the original base mixer, they must now be re-softened for further blending. This is accomplished using a series of jacketed holding vessels or warming conveyors that apply gentle, indirect heat, usually via hot water or steam circulating through double-walled stainless steel pipes. The temperature is carefully raised to a range of 40 degrees Celsius to 60 degrees Celsius, just enough to make the gum base pliable again without overheating or causing degradation of any of the soon-to-be added ingredients. The re-softened gum base is then introduced into a second type of mixer, often a horizontal batch mixer or a planetary mixer specifically engineered to process high-viscosity food materials. These mixers are outfitted with double sigma blades or paddle arms capable of kneading the gum base with immense force. Once the gum base begins to rotate and fold, the sweeteners are added gradually. These include powdered sugar, also known as icing sugar, glucose syrup, and sometimes corn syrup solids. Each of these sweeteners serves multiple purposes. Powdered sugar provides bulk, texture, and long-lasting sweetness. Glucose syrup contributes a softer mouthfeel and prevents crystallization. Corn syrup solids help maintain chewiness and shelf stability. In some formulations, especially those designed for sugar-free bubblegum, bulk sweeteners such as sorbitol, xylitol, or mannitol are used in place of sugar. These polyols require different handling due to their moisture absorption characteristics and sensitivity to heat. In any case, each type of sweetener must be fed into the mixer in stages, allowing the gum base to fully absorb and integrate the new material before more is added. This prevents clumping and ensures that the resulting mixture remains smooth and pliable. Industrial-scale screw feeders or vacuum conveyors may be used to introduce these ingredients directly into the sealed mixing chamber to maintain cleanliness and prevent contamination. Following sweetener addition, softeners such as glycerin and vegetable oils are introduced. These materials are essential to prevent the gum from becoming brittle over time and to give it the desirable, soft, elastic texture that bubblegum is known for. The quantity and timing of softener addition are precisely calculated. Too little and the gum will harden quickly after production. Too much and it will become greasy and sticky, especially under warm storage conditions. Glycerin, in particular, helps trap moisture within the matrix of the gum and acts as a plasticizer, allowing the final product to retain its chew even after prolonged shelf life. Once the bulk of sweeteners and softeners are integrated, it's time for one of the most delicate and carefully timed steps in the entire production line: the addition of flavorings and colors. Flavor compounds used in bubblegum are typically a blend of fruit, esters, vanillin, and long-lasting artificial flavors engineered specifically for gum applications. These flavors must be oil-soluble and thermally stable, as any degradation can result in bitterness, loss of intensity, or altered taste profiles. The most iconic bubblegum flavor is a blend of banana, cherry, cinnamon, clove, and wintergreen, artfully balanced to create that familiar pink taste that people associate with classic bubblegum. These flavoring compounds are often concentrated liquids or emulsified pastes, and they're introduced in the final stages of mixing to preserve their volatile aroma compounds. If added too early, the heat and shear of the mixer could evaporate or chemically alter them. The flavors are poured in slowly while the mixer runs at a reduced speed, allowing gentle incorporation. Some manufacturers use pre-encapsulated flavor beads that dissolve slowly during chewing, extending flavor release over time. Coloring agents are added simultaneously or immediately after. These are usually food-grade dyes, such as Red 3 or Red 40, depending on regional regulations, and are added in liquid form or as pre-dispersed powders. These colorants are not just about visual appeal, they help consumers identify and associate flavor with appearance. For classic bubblegum, the universal hue is a bright bubblegum pink. The dye must be evenly distributed throughout the batch, and to do this effectively, the mixer must achieve total homogeneity without overworking the gum or exposing it to heat that could cause the color to fade or change. During this final blending stage, the entire gum mass is constantly monitored. Operators inspect the mixture for uniformity, gloss, elasticity, and color consistency. Samples may be extracted from the mixer at regular intervals and manually kneaded or stretched to ensure no streaking or spotting. Texture and pliability are tested by compressing and stretching a small piece by hand or using mechanical texture analyzers. If any inconsistency is found, whether it's too stiff, too soft, uneven in color, or lacking in flavor, the batch may be reprocessed or scrapped entirely, depending on the deviation severity. Once the gum reaches the desired final formulation, it's discharged from the mixer onto a temperature-controlled rolling table. At this stage, the gum has taken on its familiar look and feel: soft, elastic, vibrantly colored, and bursting with aroma. However, it's still a massive block of uncut material, far from the small, uniform pieces sold in stores. To prepare it for shaping and portioning, the gum is flattened using motorized rollers that compress it into thick sheets. These rollers are heated just slightly, enough to keep the gum pliable, but not so hot that it becomes sticky or begins to sag. The sheeted gum is then conveyed into a sizing line, where it passes through multiple sets of progressively narrower rollers to reduce the sheet thickness to the exact target for the final product. Whether the gum will be cut into strips, rolled into tape, molded into spheres, or formed into pillow-style pieces depends on the final product format. The sheet thickness must be precise. Too thick, and the gum will be too large to chew comfortably. Too thin, and it will tear or lack substance. Precision slitter blades then slice the gum into long ribbons, which are cooled again on conveyor belts using ambient air or chilled tunnels. These ribbons are stacked and allowed to rest briefly in temperature, dent, and humidity-controlled zones. This rest period, sometimes called the conditioning phase, allows moisture and elasticity to equilibrate across the entire piece of gum. It helps stabilize the internal structure and prepare the gum for cutting, shaping, and packaging without causing cracking or deformation. At this point, bubblegum is fully formed in its raw shape, but still unwrapped and unpackaged. The product is ready for the next phase, which involves high-speed forming machines, wrapping systems, and final packaging lines designed to handle thousands of pieces per minute. These systems require their own precise engineering and synchronization to maintain the integrity and appeal of the final product. Now that the bubblegum has been properly flavored, colored, sheeted, and rested, it enters one of the most mechanically intricate and visually satisfying stages of production: shaping and cutting. At this point, the gum exists in long, flat ribbons of pliable, glossy material, carefully rolled and stacked in conditioned zones to ensure uniformity and stability. These ribbons are conveyed in single file onto a forming line that uses high-speed, synchronized mechanisms to turn raw sheets into the iconic forms consumers recognize, whether small pillow-style pieces, sticks, chunks, tape rolls, gumballs, or extruded logs. Let's first explore the most common format, the pillow-shaped bubblegum piece. This format is familiar from vending machines, Halloween candy mixes, and individual wrappers. To achieve this, the bubblegum ribbon is fed into a forming wheel, where it is gently guided through a series of progressive molds or cavity rollers. These rollers are designed with alternating male and female cavities that press into the gum from both sides, creating the shape of a small rectangular block with softened edges. As the ribbon passes through these molds, the gum is compressed and cut simultaneously by a synchronized die cutter positioned just after the final molding wheel. Cutting must be done with extreme precision, as even a millimeter of deviation could affect packaging alignment and product weight. To account for thermal expansion and gum elasticity, the cutting blades are adjustable in both depth and cycle timing. High-speed optical sensors detect the flow rate of the gum ribbon, feeding data into a digital controller that dynamically calibrates the cutter's speed in real time. The gum, now formed into uniform bite-sized pieces, is ejected onto a short conveyor, ready for wrapping. In the case of bubblegum stick formats, like the flat rectangular pieces found in classic packs, the shaping process is slightly different. Instead of molding with rollers, the gum sheets are trimmed on all four edges to create clean, sharp lines. They are then passed through a rotary cutter equipped with hardened steel blades, slicing the sheet into strips of exact dimensions. These strips are stacked and cut again to create individual sticks. The machines responsible for this operation resemble guillotines, but with servo-controlled precision that allows for continuous, non-stop operation at high speeds. The final sticks are conveyed into wrapping units without any manual handling, preserving hygiene and maintaining throughput. Bubblegum tape, a novelty format often rolled into small plastic canisters, requires its own unique process. The sheeted gum is passed through a winding station where it is gently rolled into a flat coil, not unlike a roll of tape. Tension is carefully controlled here, too much pressure, and the coil will deform or stick to itself. Too little, and it will unravel inside the container. Once coiled, the tape is automatically dropped into a custom-formed plastic shell, usually hinged with a pop-top lid. A blade inside the lid allows consumers to tear off a desired length. These plastic cases are injection molded on-site or sourced in bulk and fed into the filling line by vibratory bowl feeders. For gumballs or spherical bubblegum formats, the production method is even more specialized. Instead of being formed from ribbons, these are made using extrusion and spheronization techniques. Warm gum is extruded through a nozzle into a thick rope, which is then cut into small segments by a rotating knife. These segments are dropped into rotating pans, lined with friction-inducing surfaces that tumble the gum continuously, rounding the pieces into spheres through centrifugal motion. Once the balls reach a near-perfect shape, they are cooled and coated in a separate process, which we'll explore shortly. Regardless of the final shape, all bubblegum formats at this stage are unwrapped and uncoated, meaning they are vulnerable to sticking, moisture absorption, and contamination. Therefore, the next critical phase is the wrapping and packaging process, which combines high-speed automation, material engineering, and branding considerations. Starting with pillow pieces and sticks, the gum is immediately conveyed into primary wrapping machines. These are high-speed horizontal or vertical flow wrappers, capable of wrapping hundreds of pieces per minute. A continuous roll of printed film, typically made of polypropylene or foil-backed paper, is unwound and fed through the machine. As the gum pieces travel along a conveyor, the film wraps around each piece and is sealed using heated crimpers that create a back fin seal and two end seals. For some classic styles, twist wrapping machines are used instead, which pinch both ends of a small rectangular wrapper and twist them tightly around the gum. These machines are equipped with sensors that detect gum position and length, ensuring perfect alignment between the product and its printed branding. If even a single wrapper is misaligned or improperly sealed, that piece is ejected from the line via pneumatic diverters. Wrapped pieces are then collected, counted, and transferred in bulk to secondary packaging machines. Secondary packaging is where individual units are grouped for retail sale. For stick gum, this may involve stacking 5 or 10 wrapped sticks into a flat paperboard sleeve, then shrink wrapping the pack. For pillow gum, machines automatically count the desired number of pieces and drop them into a pre-formed bag, which is then sealed using heat or ultrasonic welders. Packaging films are chosen for durability, oxygen resistance, and visual appeal, and often include tear notches or resealable zippers for convenience. In the case of bubblegum tape, filled plastic canisters are labeled and moved through a shrink sleeve applicator, which places a heat shrink label around the container. This sleeve serves both branding and tamper-evident functions, and is tightened using a controlled burst of steam or radiant heat. Finally, canisters are packed into display boxes or larger cartons using robotic pick-and-place arms. Now we return to gumballs, which undergo a unique finishing step: sugar coating. Unlike other formats, gumballs are coated in a hard, shiny shell that not only protects the gum inside, but also adds flavor, color, and gloss. This process is performed in large stainless steel coating pans that slowly tumble the gumballs while successive layers of syrup and powdered sugar are applied. The syrup typically contains water, glucose, and food coloring, which adheres to the surface of each gumball. Then a layer of sugar or sugar alcohol-based powder is sprinkled over the syrup, sticking to it and gradually building up a thick shell. Each coating layer must be dried before the next is added. Warm air is blown gently into the pans while the gumballs tumble, ensuring even drying without cracking or warping the shell. After multiple layers are built up, sometimes more than a dozen, the gumballs are ready for polishing. This final step involves applying a thin layer of food-grade wax or shellac to the gumballs to create the glossy, reflective finish that's so iconic. The polished gumballs are then cooled, inspected, and fed into bulk bagging or capsule dispensing systems depending on their final use. Throughout the forming, wrapping, and packaging process, real-time quality control continues at every junction. Vision inspection systems verify wrapper alignment, seal integrity, and color consistency. High-speed check weighers ensure that every package contains the correct number of pieces and meets the stated weight. Metal detectors and X-ray systems scan for any foreign particles or processing defects. If a flaw is detected, the package is automatically ejected and flagged for review. And behind all of this automation is a digital infrastructure tracking every batch, from base production through to final packaging. Every piece of bubblegum can be traced back to the exact shift, mixer, raw ingredient lot, and even the machine operator responsible for that run. This traceability system is essential for food safety, quality assurance, and regulatory compliance. Once bubblegum has been fully processed, formed, wrapped, and inspected, it enters the final phase within the factory: storage, quality verification, and preparation for shipment. Although the gum is now finished, it still requires careful handling to ensure that its quality and integrity remain intact all the way through to its final retail destination. The post-production environment is just as controlled as the manufacturing zones. Finished goods are transferred into climate-regulated storage areas, where temperature and humidity are strictly maintained to preserve the texture, flavor, and packaging condition of the gum. Each product pallet is labeled with QR codes or barcodes that carry essential traceability information: product type, batch number, production date, and expiration code. These codes integrate with warehouse management systems that organize inventory by shelf life and destination. The warehouse operates on a strict first in, first out (FIFO) system to make sure the oldest products are shipped first, reducing waste and ensuring consistent freshness in the marketplace. Before any product is released for shipping, quality control teams perform final checks. Samples from each lot are pulled and tested for packaging seal integrity, gum softness, visual consistency, and flavor. Any package that fails inspection is flagged, and the rest of its batch is reviewed. All quality records are logged digitally, tying back to the original gum base formulation and mixing parameters. This robust traceability ensures that, in the rare event of a defect or recall, every package's full production history is instantly accessible. Once cleared, the products are palletized and prepared for outbound delivery. Some are shipped to retail distributors, others to vending machine companies, export terminals, or wholesalers. Trucks used for transport are checked for cleanliness and proper loading temperatures to ensure the gum isn't exposed to heat or humidity during transit. Stretch-wrapped pallets are loaded according to weight and stability guidelines, scanned out of the factory system, and then dispatched. Even after leaving the facility, each batch of bubblegum remains traceable, monitored, and accountable. This level of post-production oversight is essential to maintaining brand reliability and consumer trust. It ensures that the bubblegum purchased in a corner store, supermarket, or theme park tastes exactly as intended: sweet, chewy, stretchy, and perfectly made. From polymer blending and base formulation to flavor integration, shaping, wrapping, and final logistics, the entire bubblegum production process is a seamless combination of food science, mechanical precision, and quality management. It's a surprisingly complex journey for a product designed to be fun and carefree, proof that even the most playful confections are supported by a foundation of serious, sophisticated industrial engineering.